I mentioned this briefly in my last video about the number line, but I want to go into a little more detail about integers, decimals, and fractions. The integers are the whole numbers that you see as tick marks on the number line. But in between each of these integers, you have these large spaces that you can't describe with just integers. You have to use other numbers to represent the space in between the integers. And to do that, we have decimals and we have fractions. Now, any number between two integers can be represented both as a fraction and as a decimal. To demonstrate this, I'm just going to enlarge essentially this section of the number line right here. So this section of the number line is now going to be represented right here. We have 0 over here and 1 over here. And we have this massive space in between where there are no integers. So to describe this, as I mentioned, we have decimals and we have fractions. I'll describe fractions first. Fraction is essentially a way to divide up this section inside of here into equally spaced segments. So if we put one right in the middle, we've cut it in half or into two pieces. So two pieces, so we have a 2 on the bottom of our fraction. If we just go one of those two pieces, we have 1 over 2, or 1/2. And that is what this point here is. If we want to go further, we can divide it up into 4 segments. Now we have 4 equal segments. If we decide we want to go 1, 2, 3 of those segments, we can write this as a fraction with a 4 on the bottom because there's 4 parts, and we've gone 3 of them. So we write this as 3/4. And so you may notice that if you go 2/4, that's the same as going 1/2. So 1/2 and 2/4 are the same thing. And so this is kind of the idea of fractions. You divide up the space between the integers into equal parts, and you put that number on the bottom, or the denominator of the fraction. And then the number of those parts that you're counting is the number on the top of the fraction. And I've divided this up into 2 and then 4 because that's easy to draw. But you can divide up the space between the integers into as many sections as you like. You can divide it up into 3, you can divide it up into 5, 7, 10, any number of parts. And that's the number that'll go on the bottom. This provides a good transition into decimals. A decimal representation is essentially dividing up the space between 0 and 1 into 10 different segments. So I'll go ahead and see if I can draw that up a little bit. But so we've got 5 from here to here, 1, 2, 3, 4, 5, and then 6, 7, 8, 9, and 10. All right, so you've got the space between 0 and 1 divided up into 10 parts. With decimals, though, instead of saying, for instance, instead of writing this as 3/10, which is a valid way to write this particular point as a fraction, you would write this as 0.3. Because we use the decimal system, every number place to the right of the decimal means you've divided up this space between the two integers into 10 equal parts, and this is how many of the parts we're talking about. So we take the integer immediately beforehand and then count forward 3 of the 10 parts, and that gives us 0.3, which is the same as 3/10. And so you can take the space between any of these integers. For instance, if you wanted to take the space between 3 and 4 and count 6/10 of the way from 3 to 4, you would write this as 3.6, because you've gone 6/10 of the way from 3 to 4. And so you can describe any number on the number line using decimals or fractions. If you want to get even more specific than tenths, you can divide up, for instance, if you wanted to go somewhere between 0.3 and 0.4, you could divide this space up here into 10 equal parts, and then however many of those parts you went forward from 0.3, you would write that as another decimal here, so 0.3 and however many parts. So that is a quick overview of integers, decimals, and fractions. In this video, I want to discuss improper fractions and mixed numbers. Just to review real briefly, a fraction has a numerator and a denominator. And the denominator represents how many parts we're breaking up the whole into, and the numerator, the top number, represents how many of those parts we're counting. So if we say 3/4, it means we've broken up this whole, whatever it may be, into 4 equal parts, and then we're considering 3 of them. So for instance, I've shaded 3/4 of this rectangle here. So that's fractions. When a numerator is smaller than a denominator or less than a denominator, we have what's called a proper fraction, because the value of the fraction is between 0 and 1. So 3/4 is a good example of a proper fraction. If the numerator is larger than the denominator, for instance, if we have 5/4, this is what's called an improper fraction, because its value is greater than 1. So for instance, if we were to try to draw this, and we had this same rectangle, divided it up into 4 parts, we could shade 1, 2, 3, 4, and then we run out, and we have to draw a whole nother rectangle to shade that 5th part. And so this is considered an improper fraction. It just represents a number that's greater than 1. And so it's not really an ideal way to write this quantity. Oftentimes what you'll see when you have a quantity like this, where it's greater than 1, you'll see what's called a mixed number. This is a whole, so we can call that 1. And this over here is another 1/4. So the way you'll see this written commonly is 1 and 1/4. It's called a mixed number because you have an integer part mixed with a fractional part. And so essentially what you're saying is 1 plus 1/4 or 1 and 1/4 when you have this sort of number. Now you can convert between improper fractions and mixed numbers pretty easily, and so I'll demonstrate now how to do this. Let's take, for instance, 2 and 4/5. So this is a mixed number, and we want to convert it now to an improper fraction. So to do that, we take the denominator, 5, we multiply that by the whole, by the integer here, or the whole number, 2. So we have 5 times 2, which is 10, and then we take that product and add to it the numerator. So 10 plus 4 is 14. And so then we write 14 as our new numerator, and we keep 5 as the denominator. And so 2 and 4/5 is the same as 14/5. If we want to go in reverse, we just have to do this process backwards a little bit. So let's say we have 12 over 9. What we got to do is divide 12 by 9. 9 only goes into 12 one time, so we take out 1 as the whole number, subtract 9 from 12, and we're left with 3. So 12/9, or 12 minus 9, is equal to 3. So we've taken out the whole, and we've got the 1 here, and so what we're left with is 3 of our original 12. And so we can write that as the remaining fraction here. We have 1 3/9. And so that is how you convert an improper fraction to a mixed number. In this video, I'm going to talk about ratios and percentages. Now, a ratio is a way to compare two different quantities to one another. So, for instance, let's take marbles. If we have 20 red marbles and 25 blue marbles, we can say that the ratio of red marbles to blue marbles is 20 to 25. And so this is what ratio notation looks like. You have a number that represents the first quantity, and then a colon, and then a number that represents the second quantity. And so this right here is not a proper ratio because you can reduce it to a smaller number representation of the same idea. So anytime you have two numbers in a ratio that can both be divided by the same number, it's not yet in a proper ratio format. So 20 and 25 can both be divided by 5. If we divide 20 by 5, we get 4. And if we divide 25 by 5, we get 5. So the true ratio of red marbles to blue marbles is 4 to 5. So that's kind of how ratios work. Percentages are also a way to compare two different things, but generally these are used to compare a part of something to the whole. So let's say that in this bag of marbles we also had 5 white marbles. So that means that the total number of marbles in the bag is 20 plus 25 plus 5, or 50. So 50 marbles in the bag as a whole, and there are 20 red marbles. So we might wonder, what is the percentage of red marbles in the bag? Generally, the way you want to approach this is you want to create a fraction and then convert it to a percentage. So if we have 20 red marbles, that'll be our numerator. And we said we had 50 marbles in the bag as a whole, so that will be our denominator. So 20 red marbles, 50 total. So this is our fraction of red marbles to total marbles. In order to make this a percentage, we'll have to multiply top and bottom by 2 to get the denominator equal to 100. So we'll multiply this by 2 over 2, and that'll give us 40 over 100. Now, a percentage is just another way to represent a fraction where the denominator is 100. So if we say 40%, that's the same as saying 40 100ths. So the percentage of red marbles in the bag is going to be 40%. And so this is how you write a percent. You write a number and then this symbol, and that denotes 40 hundredths, 40% of the whole. And so that is how you can use ratios and percentages for simple things. Since this is an overview of all the foundational concepts, I want to devote a little bit of time to the 4 basic operations. In this video, I'm going to discuss how to perform addition and subtraction with large integers, decimals, and fractions. So first, large integers. Let's take, for instance, 248 and 135. So first, to add these together, what you want to do is you want to line things up at the decimal point. In this case, the numbers don't have anything past the decimal point, so you just line them up at the ends. You then start from the right and you add vertically. So we have 5 plus 8, that's equal to 13. And so we can't fit 13 in this single decimal place here, so we'll write a 3 and carry the 1. And so now when we go to add this column, we have 3 numbers in the column. And so we have to add 1, 4, and 3. And so together those are 8. And then we add 2 and 1 in the final column to get 3. So that's addition. Let's try out these same two numbers with subtraction. So we'll have 248, but this time minus 135. We'll subtract 5 from 8. 8 minus 5 is 3. Then we move to the next column. 4 minus 3 is 1, and 2 minus 1 is 1. And so that's subtraction with integers. Next, we'll go ahead and move on to decimals. Decimals are going to work largely the same way as integers, but with decimals, you have to be careful to line up the decimal points so that you're adding and subtracting in the right columns. So let's take 0.435 and we'll add 0.019. And so I've already done it here, but if you don't already have it lined up, what you want to do is line up the decimals, as I was mentioning back here. Line up the decimals vertically, so that way you know you have the right place values lined up. So we'll have 5 plus 9, which is 14. Again, we can't put 14 down here, so we have to carry the 1. Now we have 1 plus 3 plus 1, that's equal to 5. And then over here we just have 4 and 0, so we'll write a 4. And so now that we've added these, we need to make sure the decimal point drops in the right spot, and we'll add a leading 0. And so this is addition of decimals. We'll once again take the same two decimals and do subtraction. So 0.435 minus 0.019. Now we have 9 minus 5. Unfortunately, that's a negative number, so we have to borrow a 1 from over here. So this 3 is going to become a 2, and this 5 is going to become a 15. And so now we have 15 minus 9, and that gives us 6. 1 minus the 2, because we borrowed the 1 for the 15. 1 minus 2, or 2 minus 1, is 1. And then 4 minus 0 is just going to be 4. And once again, we'll drop the decimal and add the leading 0. And so this is integers and decimals, and those are both pretty straightforward. But then we have fractions. Fractions are easy enough if the denominator is the same. If the denominator is not the same, you have to convert one or both of the fractions to a different denominator before you can add or subtract them. So let's take, for instance, 1/3 and 1/6. We'll use these as our example this time. So 1/3 plus 1/6. We can't just add them together because the denominators are different. What we have to do is get a common denominator between the two fractions. To do that, you find the least common multiple of both of the denominators. In this case, the least common multiple is 6, because 6 and 3 both go into 6 evenly. 3 goes into 6 two times, so we'll need to multiply 1/3 by 2 over 2, and that gives us 2 over 6. And so now what we have is 2 over 6 plus 1 over 6. Now that the denominators are the same, all we have to do is add the numerators together, and then we retain the same denominator as both of the fractions. So we have a 6 in the denominator, and 2 plus 1 is equal to 3. And so we have 3 over 6. So that's addition. We've already done the hard part of converting the two fractions, or of achieving a common denominator between the two fractions. So for subtraction, all we have to do is write the converted form. We have 2/6 minus 1/6, and just like we did above, we'll retain the 6 in the denominator, and then we'll just use subtraction on the numerators. So 2 minus 1 is 1. And so that is addition and subtraction for integers, decimals, and fractions. In this video, we're going to look at the last two of the basic operations, multiplication and division. So to start with, let's take the case of integers. Let's take 74, 41, and let's multiply it by 7. All right, so we want to line up the two numbers at where the decimal point would be, right there. And then starting with the digit farthest to the right in the bottom number, in this case there's only one, but starting with that digit, we'll multiply by all the digits in the top number, starting with the one on the right. So we have 7 times 1, which is 7. 7 times 4, which is 28. So we'll put an 8 here and write a 2 up here. 7 times 4 is once again 28. But we have to add this 2, so we have 30. So this becomes a 0, and we add a 3 up here. Then we have 7 times 7, which is 49. Adding 3 more, we get 52. And so we can put the 5 in there. So that's multiplication for integers. If we had more digits in the bottom number, once we had finished multiplying the top number by this digit, we would then move on to this digit and multiply all those numbers, but start in this, this digit place, and then add up all the results at the end. But we just had one, so that's the answer. Division is a little bit more complicated. The way to do division, I'm going to be showing a method called long division. You write the number that you're dividing, and then to the left of that, you write the number you're dividing it by. And so in multiplication, we worked from right to left, but in division, we work from left to right. So we're going to take the digits individually if we can, and see how many times this number is going to fit into them. So first we have 7 going into 7. 7 can go into 7 one time, and 1 times 7 is equal to 7. So when we subtract this number from that number, we just get a 0. And so then we move on to the next digit. And I'll write a 4 here. 7 cannot go into 4 any times, so we'll write a 0 here, and we'll add the next digit. So 44 now. 7 can go into 44 6 times, so we'll write a 6 here. 6 times 7 is 42, and when we subtract that out, that leaves us with a remainder of 2. And so now we drag in the last digit, which is a 1. So we have 21, and 7 goes into 21 3 times. So 3 times 7 is exactly 21, and so we have a remainder of 0. So this is the full solution to this division problem. If 7 had not evenly gone into the last number here, we would have had to put a decimal point here and keep on going until it either terminated or we found a repeating pattern of digits, at which point we could stop. So this is multiplication and division for integers. I also want to demonstrate multiplication and division for fractions. It's much simpler particularly than the long division here. It's really just two different forms of multiplication. So let me demonstrate that. Let's say we have 1 over 3 times 3 over 4. Now, all we have to do to multiply fractions, we don't have to worry about common denominator or any of that like we do with addition and subtraction. We just multiply the two numerators. 1 times 3 gives us 3. And then we multiply the two denominators. 3 times 4 gives us 12. And so it's a lot easier in one sense to multiply two fractions than it is to add or subtract. And so that's really all there is to fraction multiplication. Fraction division just requires one extra step. And so what it's going to look like is if you have 1/3 divided by 3/4, that you you take the reciprocal of the second number and then change the division sign to a multiplication sign. So this becomes 1 over 3 times, this was 3 over 4, so we'll take times 4 over 3. And so we flipped the fraction and changed it to a multiplication. And then all we have to do is just multiply numerator and denominator like before. 1 times 4 is 4, and 3 times 3 is 9. And so that is a brief review of multiplication and division for integers and fractions. In this video, I'm going to talk about exponents and roots. An exponent is a number that tells you how many times to multiply the base number by itself. So for instance, if we have 2 raised to the second power, like this, what this is telling us is that we need to multiply 2 times 2. Now if we had 2 raised to the third power, this would be the same as 2 times 2 times 2. So the exponent is saying how many times to multiply this number by itself. A root is kind of the opposite of this. So let's take, for instance, 16. This is a radical symbol, and this tells us that we're taking a root. If there's no number up here, the number is assumed to be 2. So without any numbers up here, the radical sign designates a square root, or a root to the power of 2. So the square root of 16 is the number that has to be multiplied by itself twice in order to equal 16. So the square root of 16, by definition, if it is squared or raised to the second power, it equals 16. And so the square root of 16 is 4, because 4 raised to the second power, or 4 times 4, is equal to 16. And so roots and exponents are kind of inverse operations. But you can actually express roots as exponents. So for instance, if we wanted to go back to the square root of 16 here, we can write the square root of 16 as 16 to the 1/2. And so essentially, if you have 1 over a number in the as an exponent, you're essentially taking that number's root of the number in question. So like I was saying, the 2 up here that's omitted for a square root, that's the same as 1/2, a power of 1/2. You can also have other fractions or other powers of roots. So for instance, you might take 8 to the 1/3, or the third root of 8. So this would be a number that you have to multiply by itself 3 times in order to achieve this. So the third power of 8 raised to the third power is equal to 8. And so this number would be the same as 2, because 2 times 2 times 2, or 2 to the third power, is equal to 8. And a couple other things about exponents. Any number raised to the 1 is just the number itself. So 2 raised to the 1 is just 2. And any real number raised to the 0 is equal to 1. It doesn't matter if it's a positive number or a negative number. Any real non-zero number raised to the power of 0 is equal to 1. You may notice that all of the exponents and roots we've looked at so far here are whole numbers, or fractions of whole numbers. You can, in fact, have roots that are, for instance, say this is 2 raised to the 2.3. You can have this sort of quantity, but it's not going to be easy to calculate by hand, and really you're going to want to use a calculator if you encounter anything that has a decimal in the exponent. So that's a good overview of exponents and roots. I've talked a little bit about equations so far, but now I want to give some definition to the term. An equation consists of two mathematical expressions separated by an equal sign. So for instance, we might have an equation that says 1 plus 1 equals 2. And this is true because this value is the same as that value. Now the beauty of equations is that you can perform any operations the same way on both sides of the equation, and the equation remains true. So for instance, we can add 5 to both sides of this equation, and the equation is still true. We can multiply both sides of the equation by 7, and the equation is still true. We can divide both sides of the equation by 13, and this equation is still true. And so anything you perform on both sides of the equation equally do not invalidate the equation. Similar to equations, we have what's called an inequality. So we might have the inequality 1 is less than 2. And so this consists of a mathematical expression on one side and a mathematical expression on the other side, and a sign that indicates which side is greater or lesser. So that's what we have here. This is read as 1 is less than 2. And similar to equations, we can perform the same operations on both sides of the inequality sign, and it can remain true. So again, we can add 5 to both sides, and it's still true. 6 is still less than 7. We can multiply both sides by 7, and it's still true. This side is now 42, and this one is equal to 49, so it's still true. And we could divide it by 13, and it's still true. The one thing that we can't do with inequalities without changing them, that we can with equations, is multiplying or dividing by a negative number. So if we wanted to multiply both sides of this inequality by -1, that would make it untrue. Because in the most simple of examples, if we have an equation that says 1 is less than 2, and we multiply both sides by -1, that becomes -1 is less than -2, which is not true. So what you have to do, if you multiply or divide both sides of an inequality by a negative number, what you have to do is reverse the inequality sign. And so this is now a valid inequality once again, because we switched this sign after multiplying by -1. To show in real simple terms what that looks like, if you have 1 is less than 2, and then you want to make it negative, you can say -1 now is greater than -2. And that is the true expression of the inequality. And so you can have greater than or less than, and you can also have a greater than or equal to, which is something of a combination of equations and inequalities. So we would write greater than or equal to as a greater than sign with a line under it. And similarly, less than or equal to would be less than with a line under it. And so this is kind of a more formal definition of equations and inequalities and what you can do with them. When you combine absolute values and inequalities, things can get complicated very quickly. So I want to look at just a couple of basic examples of some inequalities that contain absolute values. So perhaps the most basic you can find is just an absolute value of x that is less than a constant. We'll say 3. So if the absolute value of x is less than 3, that means that we need to solve it two different ways. First, with x as a positive number, which gives us x is less than 3. And then secondly, with x as a negative number, which gives us negative x is less than 3. Or multiplying both sides by -1 and flipping the sign, x is greater than -3. And so we have these two solutions, and they both must be satisfied. So we have a range of values for x. We say that x is greater than -3 but less than 3, or x is between -3 and 3. And so this range of values for x is the solution to that inequality. And it's bounded because the absolute value is given an upper maximum. We're going to look in this next example here at a situation where the absolute value of x is greater than a constant. And so if the absolute value is greater than a constant, that means that x can be either positive or negative and extend to infinity in either direction and still satisfy this equation. So whereas in this one we had two finite bounds, here we're going to have two infinite bounds. So we'll go ahead and solve this with a positive x first. We get x is greater than 3, and so that's one option for a solution. And then assuming x is negative, we can have negative x is greater than 3, or multiplying by -1 and flipping the sign, x is less than -3. And so now we have two ranges, bounded on one side by 3 or -3, and bounded on the other side by an infinity. So x can be between 3 and infinity, or between -infinity and -3. And so these are the two ranges of x that satisfy this inequality. Now there's one more example I want to look at real briefly, and that is the example of a no solution problem. So suppose we have x, the absolute value of x plus 3 is less than 2. Now if we try to solve this, we'll subtract 3 from both sides, and that'll give us absolute value of x is less than -1. And so we can look at this and we can see that there's going to be no solution, because the absolute value function tells us that this side of the equation is going to be positive. And so if we have a positive number here that has to be less than -1, that just doesn't work. There's no value for x that'll satisfy this equation. And so when you have absolute values and inequalities, these are three of the things you can encounter. In this video, I want to take a brief detour from algebra to look at a geometry application for what we just talked about, meaning the topic of equivalent ratios. Now in geometry, you have a property of triangles called similar triangles. And when you have two triangles that are similar, you know that the ratios of their corresponding sides are equal to one another. And so you have a multiple equivalent ratio problem. So let's say we have two triangles. Let's say this first triangle, this isn't going to be drawn to scale, but let's say we have triangle ABC and triangle XYZ. And so these two triangles, we're told that they're similar. And so what that tells us is that side A, the ratio of side A to side X, is the same as the ratio of side B to side Y, which is the same as the ratio of side C to side Z. And so if we're given the lengths of the sides on one of the two triangles, and then the length of any one side on the other triangle, we can find the missing quantities. And so let's say we're told that triangle ABC has sides of length 4, 3, and 2. And then we're told that side X is equal to 12. So we have these four quantities and we need to find the remaining two. We can use equivalent ratios to find their values. So we have the value for x, so this will be the ratio we use to find the exact value of the ratio. And so a is equal to 4 and x is equal to 12. And so this ratio is the same as 1 over 3. And so b and y are going to have a ratio of 1 to 3, and c and z are going to have a ratio of 1 to 3. And so we can set up two more of these, two more equivalent fraction problems to find the values for y and z. So b over y, or 3 over y, is going to be equal to 1 over 3. And now we can cross multiply to find the value of y. We get 3 times 3 is 9, and y times 1 is y. So the value of y is 9. We can do the same thing now with c and z. We know the value of c is 2, so 2 over z is equal to 1 over 3. When we cross multiply, we get z equals 6. And so this is just one example of an application of equivalent ratios in geometry. As I mentioned in the last video, a single linear equation can't be solved for specific values of x and y. It can only be solved for one variable in terms of the other variable. What that leaves us with, though, is a set of solutions, an infinite set of solutions that will satisfy the equation. So let me show you what I mean by that. Let's say we have the linear equation y equals 2x minus 1. Now we could plug any value of x into this equation and it would generate a value of y for which the equation would be correct. And so what you have is, as I mentioned, an infinite set of pairings that satisfy the equation. And we can represent that graphically with a line, because a line extends infinitely in both directions. And so by graphing a line, we can show graphically that any point on that line is a set of values for x and y that will satisfy a given equation. So this equation here can be graphed by substituting in for x a value of x and seeing what the resultant y value is and plotting that point, then plugging in a second value for x, getting a second y value and plotting that point. And because each line can be defined by 2 points, that will give us the line that represents this equation. So let's start out by plugging 0 in for x. By plugging 0 in for x, we get 0 minus 1, or negative 1, so y equals negative 1 when x equals 0. So we have our x-axis and our y-axis. When x equals 0 and y equals negative 1, that's this point right here. I'll go ahead and mark this 0, negative 1. So that's one point that's on this line, and it corresponds to x equals 0, y equals negative 1, which is one set of values that satisfies the equation. But let's plug in 1 now for x and see what we get. 2 times 1 is 2, minus 1 is 1. So when x equals 1, y equals 1. And if we plot that point as well, we get x equals 1, y equals 1, and another point that's on our line is right here. So now that we have 2 points, we can plot our line because 2 points can only represent, or can only lie on, one single line. And so this is the line that is the solution set for this linear equation. Now there are a couple of features that I want to point out about a graphed line that can tell us things about the equation that it represents. So in this equation, for instance, the line crosses the y-axis at negative 1. And this is what's called the y-intercept. The line intercepts the y-axis at a particular point, in this case negative 1. And the y-axis, or the y-intercept, when you have an equation of this form, is going to be this part of the equation right here. The part of the right side of the equation that doesn't have an x next to it. So that's the y-intercept. We also have what's called the slope. Now the slope of a line is defined as the change in the vertical coordinate divided by the change in the horizontal coordinate. And so for a given interval on this line, it doesn't matter how big the interval is, but we're just going to take the smallest one that we have graphed here. For any given interval, the slope is the change in the vertical divided by the change in the horizontal. In this case, the change in the vertical is 2. We go from -1 to 1. And the change in the horizontal is 1. We go from 0 to 1. So the slope here is 2 divided by 1, or just 2. And the slope, when you have an equation of this form here, is going to be the coefficient of the x term. And so this equation here is in what's called slope-intercept form. And I'm going to talk a little bit more about that in a later video. But these are just some of the key features to note on a graph of a line. You have the y-intercept and you have the slope, and you can either use the graph of the equation to find the equation, or you can use the equation to graphically show the solution set. Linear inequalities are solved basically the same way as linear equations. They can only be solved for one variable in terms of the other. So for instance, if we have the inequality 8y minus 4x is less than 8, all we can do is solve it for y in terms of x, or x in terms of y. So let's solve it for y in terms of x. We'll divide both sides by 8, so that will give us y minus 1/2 x is less than 1. And then we'll isolate the y by adding 1/2 x to both sides. Adding 1/2 x to both sides. And that gives us y is less than 1/2 x plus 1. So now we have our inequality essentially in point-slope format. And so you can also graph inequalities in basically the same way as equations. We still have a slope and a y-intercept. And so we can graph our points here. We know that there's a point right here because it crosses the y-axis at 1. And we know that it has a slope of 1/2, which means that for every 1 unit it moves to the right, it moves half a unit up. Or for every 2 units it moves to the right, it moves 1 unit up. So we can plot a second point for this line by moving 2 units to the right and 1 unit up. And so our second point for the line is going to be up here at 2, 2. And this first one was at 0, 1. And so these are the 2 points for the line. And so let's go ahead and draw the line through these points. This is the line that represents what this would be if it were an equation. But because this is an inequality, y is less than this quantity. To graphically show the solution set for a linear inequality, instead of a line, we have a region, in much the same way that with a single variable inequality, we had a range of values instead of a single value. So here we have a region of y that satisfies the equation for every given x. And that region, because y is less than this value, is everything where y has a lesser value than this line. So anything below this line, everything down in this region, satisfies this inequality. And so this is kind of how you can graphically show the solution set for a linear inequality such as this. The last type of graph I want to look at before we move on is the graph of the absolute value equation. Now let's take the absolute value equation of y equals absolute value of 2 minus x over 2 plus 1. And so if you'll recall, when we solve absolute value equations, we have to solve them twice, essentially. We have to first assume that the value inside the absolute value is positive, and then solve again assuming that it's negative. So what we're going to wind up with is two different equations of lines. And we'll have to combine them in a way that makes sense given what we know. So first let's assume that the value inside of here is positive. And that equation will just be y equals 2 minus x over 2 plus 1. If we distribute this over 2 here, we get y equals 1 minus x over 2 plus 1, or y equals negative x over 2 plus 2. And so this is the value of the equation where this term is positive. If this term is negative, we can solve the equation as y equals negative 2 minus x over 2 plus 1. And so once again, if we distribute the negative sign in the 2, we get y equals negative 1 plus x over 2 plus 1. The minus 1 and the plus 1 cancel, and we're left with y equals x over 2. And so what this tells us is that if this value is greater than 0, then this is going to be our equation of the line. And if this value is less than 0, this is going to be our equation. And so we need to figure out at what point we'll switch from using this equation to using this equation. So at what point does 2 minus x over 2 equal 0? This side of the equation is going to equal 0 when 2 minus x equals 0, or when x equals 2. So at the point where x equals 2, this is going to be where the equation switches. So if this quantity is less than 0, that's going to be when x is greater than 2, because if x is greater than 2, then 2 minus x will be greater than 0. So if x is greater than 2, we'll use this equation. And if x is less than 2, we'll use this equation. So first let's go ahead and graph the greater than 2. Y equals x over 2, and the y-intercept is 0, because there's nothing else here. So this is our point, but this point is to the left of this line, which means that anything over here isn't going to be on the actual graph of our equation, but we can use this as a reference point and say that we're going to draw the line through this point, and a slope of 1/2 up gives us 2 over 1 up this point here, 2, 1. And so the line will be in this direction, but the line of this slope won't start until it hits this point here. To the left of the line, we have to use this equation. And in this equation, we're going to have a negative 1/2 slope with a y-intercept of 2. And so the line is going to go through this point, and it's going to come downward with a slope of negative 1/2. And so we already have another point that it goes through, which is this one. And so we can draw the line back this way. And so what you can see here is that with an absolute value equation, the graph, it has a corner or a reflection at the point where the value of the term inside the absolute value becomes 0. And so you go down until you hit that point, and then up thereafter. And so this is what the graph of an absolute value equation is going to look like. Now that we've laid a groundwork for multivariable equations by looking at linear equations, I want to look at systems of equations. Now, a system of equations is a set or a group of equations where the variables in however many equations you have represent the same quantities in each equation. So, for instance, if we have the system of equations 3x plus 4y equals 10, and 4x plus 8y equals 12, we have x and y in both of these equations, and this x are the same, and this y and this y are the same. And so you have essentially two pieces of information about these variables instead of one. And the general rule is that with systems of equations, if you have the same number of equations as you have variables, you can solve for values for the variables. You'll recall with a single two-variable equation, we couldn't solve for values for x and y. We could only solve for those variables in terms of the other variable. So with a system of equations, if we have the same number of equations as variables, generally we can solve for values for those variables. Now there are two exceptions to that rule. One is if the two equations are contradictory. So for instance, if you had the system of equations x plus y equals 5 and x plus y equals 1. These two equations are contradictory because they're telling you that the same quantity, x plus y, is equal to two different things. And this obviously can't be solved for values. The other situation where you can't solve for values is if the two equations are redundant. So for instance, if we have x plus y equals 2 and 2x plus 2y equals 4. These two equations are redundant because they tell us the exact same thing. If we divide each term in this second equation by 2, what we're left with is equation 1. And so it's really no better than having just one equation. We can't solve it for the values for these two variables. One way to think about solving systems of equations, at least linear equations like this, is to think about it graphically. The definition of what we're looking for here can be shown very easily on a graph. Let's say that this first line, the graph looks like this, and this second line, the graph looks like this. And we have some x and y axis here. Let's say this is x and this is y. And this point right here is where these two lines intersect. And so this point has an x coordinate and a y coordinate. And the values of this x and y coordinate are the values for x and y that satisfy both of these equations. And so that's how you can kind of think about systems of equations graphically. And in this case here where we have the contradictory equations, this would essentially be parallel lines. The equations x plus y equals 5 and x plus y equals 1 would look something like this. You'd have these two parallel lines that never intersect. And so that's why you can't solve these for either variable. And in this case, with the redundant equations, this is as though you have one line drawn on top of another line. And so the solution for this is the entire line. So in both of these cases, there's no way to solve for x and y. But if you have the same number of equations as variables, and they're not contradictory and they're not redundant, you should be able to find what is graphically the intersection point and solve for values for the variables. In the next couple of videos, I'm going to demonstrate a couple of different methods for solving systems of equations.
Area and circumference of a circle. Area of a circle is found by multiplying pi times the radius squared. The radius of a circle is a segment that has its endpoints on the circle and on the center of the circle. Or you can think of it like it goes halfway across the circle. Circumference, which is the distance around the circle, is 2 times pi times the radius, or pi times the diameter. The diameter of a circle is a segment that passes through the center of the circle and has its endpoints on the circle, or it goes all the way across your circle. The diameter is twice the radius. Likewise, the radius is half of the diameter. These formulas are interchangeable since when you multiply 2 times the radius, you get diameter. Let's look at an example. Find the area and circumference of the following circle in terms of pi and to the nearest tenth. In our example, all they've given us is the diameter, but that's all we need to find our area and to find our circumference. We'll start with area. The first thing we're going to do is write our formula for area. Area is pi times radius squared. Now we need to substitute our radius, but they only gave us the diameter. Keep in mind that the radius goes halfway across your shape, or that it's half the diameter. Your radius is half of your diameter. So the radius is half of 22 centimeters, which means that the radius is 11 centimeters. So now we'll substitute 11 centimeters for our radius. So our area is pi times 11 centimeters squared. We need to follow PEMDAS, so we need to square our radius first, take care of our exponents first. 11 squared is 121. Centimeters squared is centimeters squared. 121 centimeters squared times pi is 121 pi centimeters squared. They asked us to find our area and circumference in 2 different ways. The first way was in terms of pi. This answer is the area of our circle in terms of pi, which means leave pi in your answer, or don't multiply times pi. So this would be one of our answers. The second way they asked us to find area was rounded to the nearest tenth. So now we do need to multiply times pi, and when you multiply 121 times pi, you get that the area is about 380.1327, etc. So since they asked us to round to the tenths place, the 1 is in the tenths place, but the 3 tells the 1 what to do. The 3 tells the 1 to stay the same, so that would be 380 1/10 centimeters squared. Circumference, we can use either one of these formulas to find. Since we were given the diameter, we can just use our circumference equals pi times diameter formula. So now we need to substitute our diameter. The circumference is pi times 22 centimeters, which is 22 pi centimeters. And that gives us the first answer they asked for in terms of pi, 22 pi centimeters. To find our answer to the nearest tenth, we now need to multiply 22 times pi so that we get circumference is 69.1150, etc. And then we round to the tenths place. The 1 is in the tenths place, and the 1 next to it tells it to stay the same. So our circumference is 69 1/10 centimeters. Area and perimeter of a triangle. The area of a triangle is found by taking half of the product of the base and the height. The base of the triangle can be any of the sides, but the height must be perpendicular to the base. The perimeter of a triangle is found by adding all the sides together. So side 1 plus side 2 plus the base, since those are the three sides. One way to remember the formula for the area of a triangle is that a triangle is half of a parallelogram. If you can imagine drawing the rest of the parallelogram out here, you can see this triangle is half of a parallelogram. The area of a parallelogram is base times height, so the area of half of a parallelogram, or a triangle, is half base times height. Now for an example. Find the area and perimeter of the following triangle. First, let's find the area. We're going to start by writing our formula for area of a triangle. The area of a triangle is half the product of the base and the height. Now we need to substitute our base and height. Area is 1/2. Again, the base can be any of the sides, but the height must be perpendicular to it. So start with the perpendicular height. Right here, the 6 inches. It's perpendicular to this base, 13 inches. Therefore, our base is 13 inches and our height is 6 inches. So we substitute 13 inches for base times 6 inches for our height. Now, since all we're doing is multiplying, we can multiply in any order. We can take half of 13 and multiply that times 6, or we can take half of 6 and multiply that times 13, or we can do 13 times 6 and then take half of that product. So it's whatever is easiest, and to me, I think taking half of 6 would be the easiest. So I'm going to start by taking half of 6 inches. Half of 6 inches is 3 inches times 13 inches. 3 inches times 13 inches is 39 inches squared. Now for perimeter. Again, we're going to start with our formula. The perimeter of a triangle is the sum of all the sides. So 10 inches plus 8 inches plus our base, 13 inches. And we can again add this in any order that we want. So maybe we start with 10 inches plus 13 inches, 23 inches, plus 8 inches. 23 plus 7 would be 30, and 8 is one more than that, so the perimeter is 31 inches. Finding measurements for parts of a circle. A pizza with an 18-inch diameter is cut into 12 equal slices. What is the area of each slice? How many linear inches of crust does each one have? What is the total perimeter of each slice? We're going to take this one question at a time. So we've cut a circle into 12 equal slices. That means that the area of our circle has been cut into 12 equal pieces. So if I find the area of my circle and then divide it by 12, I can find the area of one piece of pizza. That's the question we're starting with. What is the area of each slice? So first I'm going to find the area of my circle. Area of a circle is pi times the radius squared. They didn't give us the radius though. We were given the diameter. The diameter is the distance across the circle through the center. It has its endpoints on the circle. The radius is the distance halfway across the circle, or it has its endpoints on the center and the outside of the circle. The radius then is half the diameter. So if the diameter is 18 inches, then the radius is 9 inches. So we substitute 9 inches for radius. Pi times 9 inches squared. So the area is 9 inches squared is 81 inches squared times pi is 81 pi inches squared. Now that's the area of the whole pizza. We want to find the area of just one slice, or of each slice. So that tells us we're going to divide. The area of our pizza is cut into 12 equal slices. So we're going to take our area, 81 pi inches squared, and divide it by 12. And then we can simplify that. We can divide our numerator and our denominator both by 3, and we get 27/4 pi inches squared. So that's the area of just one slice of pizza. The next question says, how many linear inches of crust does each one have? So when they're talking about the crust, that's part of the circumference of the circle. How much of the circumference? The circumference of a circle is pi times the diameter. So the circumference of the circle is pi times 18 inches, since that's our diameter, which means our circumference is 18 pi inches. That's the distance all the way around the circle. But our circumference has been split into 12 equal slices by these 12 pieces of pizza. So if we want to find the linear inches of crust one slice has, then we take our linear inches of crust for the whole pizza and divide it by 12. So that's 18 pi inches divided by 12. And that can be simplified. We can divide our numerator and our denominator by 3. 18 divided by 3 is 6, and 12 divided by 3 is 4, so 6/4 pi inches. Or we could keep simplifying that, or we can say 4 goes into 6 one time with 2 left over, 2 out of 4, or 1/2. So it's 1 1/2 pi inches. 1 1/2 pi inches of crust for each slice of pizza. The last question says, what is the total perimeter of each slice? So perimeter is the distance around. The perimeter of a slice of pizza would be our crust part, so that's that 1 1/2 pi inches, plus this segment, which is our radius, which we found earlier was half the diameter, so plus 9 inches, plus the radius again, so plus 9 inches again. And then we would combine like terms. So the perimeter is 9 inches plus 9 inches is 18 inches plus 1 5/10 pi inches. And that would be the perimeter of one slice of pizza. Geometric symbols, angles. It's important to understand the different symbols that are associated with geometry so that when you're asked a question, you know what you're being asked and you also know how to answer. In this video, we're going to talk about the different symbols that are associated with angles specifically. So here we have two triangles, triangle ABC and triangle DEF. We're going to answer the following 3 questions, and we'll talk about what the symbols mean as we go. The first one is, name the angles in triangle ABC. There are a couple of different ways to name angles. One way is to use the angle symbol and just the letter of the vertex of the angle. So we would call this angle angle A, since A is the vertex. This angle would be called angle B. So we use the angle symbol and the letter for the vertex. The last angle would be angle C. Again, this is the angle symbol, and you name it by its vertex. The other way to name angles would be to use the 3 letters for the angle. So angle A could be called angle BAC. Notice that the vertex is in the center of the name, and we still use that angle symbol to name it. It looks very similar to the less than sign, but the bottom is straight. To name angle B, we could also name it angle ABC or angle CBA, as long as that B stays in the middle. And then angle C can be called angle BCA or angle ACB. Again, that vertex needs to be the middle letter. So we start with our angle symbol, angle ACB. So there are 2 different ways to name angles, all using the angle symbol. Next, we need to name the congruent angles in triangle ABC and triangle DEF. Congruent means the same or equal, exactly the same. And congruent angles are marked for you sometimes on pictures, and the way you'll know which angles are congruent is because they'll be marked in the same way. So since angle A and angle D have the same mark on them, that means that angle A is congruent to angle D. We used our angle symbols again, and this sign in the middle means congruent. It's an equal sign with a little squiggly on top. Angle B is marked similarly to angle E, and we're going to talk about this symbol in just a minute. Angle B is congruent to angle E. Finally, angles C and F are marked the same way. They both have these 2 marks on the angle, so that means that they are congruent to each other. Angle C is congruent to angle F. Now this last question says, what is the measure of angle B? This M stands for measure. And so when you see the M, that means they want the degree. How many degrees are in the angle? What's the measure of the angle? Angle B, even though there isn't a number there, this box means that angle B measures to be 90 degrees. So the measure of angle B equals 90. And the measure of angle E would also be 90 degrees. Proof that a triangle is 180 degrees. The 3 angles of a triangle add to be 180 degrees. There are many different ways that you can see this. One way is if you construct a triangle out of paper, make sure those lines are straight, and you tear off those 3 angles, then when you put them together, they'll make a straight line. But here's another proof of why the 3 angles of a triangle add to be 180. Here we have 2 parallel lines, line DE and line BC. And that's important. Our lines must be parallel in order for this proof to be true. And since those lines are parallel, then we can see that angle DAB and angle ABC are alternate interior angles. They're on different sides of this transversal AB, and they're inside our parallel lines. So we call those alternate interior angles. And we have a proof about alternate interior angles that says if 2 lines are parallel, then alternate interior angles are congruent. So we know that these angles are congruent to each other, which is why I've marked them each with 1 arc. Likewise, angle EAC and angle ACB are also alternate interior angles because they're on different sides of this transversal and they're inside our parallel line. So again, those angles are congruent to each other because of the alternate interior angles theorem. And then finally, angle BAC, if you put it together with these other two angles, you get a straight line which measures 180 degrees. So since angle DAB plus BAC plus CAE equals 180, then because these angles, alternate interior angles, are congruent, and these alternate interior angles are congruent, that means that the three angles inside of our triangle also add to be 180 degrees. Pythagorean Theorem. The Pythagorean Theorem states that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse of a right triangle. The legs of a right triangle are the two sides that form the right angle. The hypotenuse is the side that's across from the right angle. Let's look at two examples. Find the missing sides of the right triangles. On this first example, we're given the lengths of the two legs of the right triangle, and what we need to find is our hypotenuse. The hypotenuse, again, is the C in the Pythagorean theorem. So what we're trying to find is C. And we'll start by writing the Pythagorean theorem. A squared plus B squared is equal to C squared. A can be either one of the legs, and B can also be either one of the legs. So 4 squared plus 3 squared is equal to, and the hypotenuse is what we don't know, so we'll leave it as C, our variable that we're trying to find. Then we simplify. 4 squared is 16 plus 3 squared is 9 is equal to C squared. Then we need to combine like terms. 16 plus 9 is 25. 25 is equal to C squared. We're almost there, but we haven't found C yet. Right now we know what C squared equals, and that's 25. But to find C, we need to do the opposite of squaring, which is square rooting. So we square root both of our sides. The square root of 25 is 5, and the square root of C squared is C, which means that our hypotenuse is 5. On this next triangle, we know the hypotenuse this time. Across from the right angle is our hypotenuse, and that's given to us as 17. So what we're trying to find now is one of our legs. And this leg can either be your A or your B. So I'm going to call it my B. Again, we'll start with Pythagorean theorem. A squared plus B squared is equal to C squared. A and B are your legs, and C is your hypotenuse. So we know one of our legs, 15, so I'll substitute that for A squared, plus, we're trying to find our other leg, B squared, we don't know it, equals, and then our hypotenuse, which is our C, is 17, so 17 squared. Now we need to simplify. 15 squared is 225, plus B squared is equal to 17 squared is 289. Since we're trying to solve for B, that means we need to get B alone. And to do that, we're going to have to subtract 225 from both sides. 225 minus 225 is 0. So on the left side, we're left with B squared is equal to, and then 289 minus 225, 9 minus 5 is 4, 8 minus 2 is 6, and 2 minus 2 is 0. So again, we found B squared, but we haven't found B yet. So to solve for B, we need to take the square root of both sides. The square root of B squared is B, and the square root of 64 is 8. So that means that our other leg on our right triangle is 8. Right triangle word problem. A ramp with a 30-degree angle from the ground is to be built up to a 2-foot-high platform. What will be the length of the ramp? How far from the platform will it extend to the nearest inch? With problems like these, it's very helpful to draw a picture. So we have a ramp that makes a 30-degree angle with the ground. So let's start with that. Here's the ground. Here's our 30-degree angle. And it's to be built up to a 2-foot-high platform. So then here we have a platform, and it's 2 feet high above the ground. So there's a right angle there, perpendicular to the ground. The first question is, what will be the length of the ramp? So this is what we're trying to find. Well, before I start to find x, I first want to fill in what this angle is. You might already know that since we have a 30-degree angle and a 90-degree angle, that this angle has to be 60 degrees. But if you didn't know that, you could find it because there are 180 degrees in a triangle. So if you add 30 to 90, you get 120. 180 minus 120 leaves you with 60 degrees for that third angle. Now that we know it's a 30, 60, 90 triangle, we can apply our 30, 60, 90 rules to finding the length of our ramp. Our ramp is across from the 90-degree angle, therefore that's our hypotenuse. The side we know, the leg we know, is across from the 30-degree angle, so it's our shorter leg. And the hypotenuse of a 30, 60, 90 triangle is twice as long as the shorter leg. Our hypotenuse, again, we're using x for, equals 2 times the shorter leg, which is that 2-foot side. So 2 times 2 feet, which means x is 4 feet. Therefore, the length of the ramp is 4 feet. So we've answered the first question. Then they asked, how far from the platform will it extend? How far from the platform will the ramp extend? So now they're asking us to find that length. And y is across from our 60-degree angle, so that's our longer leg. And the longer leg of a 30, 60, 90 triangle is the square root of 3 times the shorter leg. Our longer leg, again, is y, equals the square root of 3 times, and our shorter leg is still that 2-foot length. So y is 2 square roots of 3 feet. They didn't ask us for the answer in feet, they asked to the nearest inch. So the first thing I'm going to do is convert 2 square roots of 3 feet into inches by multiplying by 12. So y is 2 square roots of 3 times 12, since there are 12 inches in 1 foot, which is 24 square roots of 3 inches. But they didn't ask for it in simplest radical form, so then we'd actually want to calculate what 24 square roots of 3 inches is, and it's about 42 inches. Therefore, how far from the platform will the ramp extend? The ramp will extend about 42 inches from the platform. There we have it. Laws of exponents. We're going to look at 7 different laws. The first is that any number raised to the first power is just itself. If you'll remember what an exponent is, it tells you how many times to multiply the base number times itself. So if you're multiplying the base number times itself, well, just one time, then that's just that number. Like 2 to the first power would just be 2. Or negative 3 to the first power would just be negative 3. The second rule says that 1 raised to any power is 1. Because all you're doing is multiplying it 1 times itself, and no matter how many times you multiply 1 times itself, it'll always be 1. So for instance, like 1 to the third power, that means 1 times itself 3 times. 1 times 1 is 1 times 1 is 1. So it doesn't matter how many times you multiply 1 times itself, you'll always get 1. The third law says that any number raised to the 0 power is 1. This is one of my personal favorites. I think it's pretty cool. Like 8 raised to the 0 power. It's just 1. Or negative 10 raised to the 0 power. Again, just 1. Or even say like a half raised to the 0 power. Still 1. Any number raised to the 0 power is always 1. The fourth law is when you're multiplying with the same bases. So notice A and A, our bases are the same, but we have different exponents. When you multiply numbers with the same bases, you add the exponents. Let's look at why. So say we were doing 2 cubed times 2 to the 4th. Well, what that really means is 2 cubed is 2 times itself 3 times, so 1, 2, 3 times, times 2 times itself 4 times, so 1, 2, 3, 4 times. So we've multiplied 2 times itself a total of 7 times. So instead of going through all of this, we can just use that rule that when we multiply numbers with the same bases, we simply add the exponents. And then you could simplify from there. The fifth rule is pretty similar to the fourth rule, except we're dividing numbers with the same bases. So instead of adding our exponents, we subtract our exponents. For example, if we were doing 2 to the 5th divided by 2 cubed, what we're really doing is 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2. So that's 2 to the 5th, 2 times itself 5 times, divided by 2 times itself 3 times. Well, we can simplify by canceling. 2 divided by 2 is 1. 2 divided by 2 is 1, and 2 divided by 2 is 1. So what we're left with then is simply 2 squared, or 4. So instead of doing this, we can use our rule that when we're dividing numbers with the same bases, we simply subtract the exponents. And that saves us a little bit of time. 2 to the 5th divided by 2 cubed, 5 minus 3 is 2, so it's 2 squared, which is 4. It also works if your denominator, the exponent on your denominator, is larger. Let's look at one of those. So that'd be like 2 squared divided by 2 cubed. So you still subtract your exponents, so it's 2 squared minus 3, which is 2 to the negative 1. And then you would simplify that by bringing this to your denominator, 1/2. The sixth rule says that when you raise a power to a power, like a to the n raised to the m, you multiply your exponents. So for instance, with 3 squared cubed, what that really means is 3 squared times itself 3 times. So that's 3 squared times 3 squared times 3 squared. 3 squared times itself 3 times. 3 squared times 3 squared times 3 squared is 3 to the 6th. So all you have to do is multiply your exponents. 2 times 3 is 6. 3 to the 6th. The 7th rule says that when you have operations inside parentheses that are raised to an exponent, then each term inside those parentheses is raised to that exponent. So, for instance, like 2 times 3 squared. That is 2 squared times 3 squared. And again, you could simplify from there. Left off my n there, that's important. Now on this next one, same thing, just with division. So a divided by b, that quantity raised to the n, would be a to the n divided by b to the n. So everything in the parentheses is raised to the n power. So it'd be like doing 4 divided by 3 cubed. So that'd be 4 to the 3rd divided by 3 to the 3rd. And then again, you could simplify. And those are our laws of exponents. Absolute value. Absolute value is the distance of a number from 0 and is always positive. It's denoted by a pair of vertical lines surrounding the value, such as the absolute value of 3. You can think of absolute value like you're being asked a question. And the question is, how far is 3 from 0? 3 is 1, 2, 3 places from 0. So the absolute value of 3 is 3. The absolute value of a negative number and its positive counterpart are the same. So the absolute value of negative 3 is also 3 because negative 3 is also 3 places from 0. 1, 2, 3 places from 0. The absolute value of a difference, when you're doing that, the order doesn't matter. Let's look at the absolute value of a couple of differences. The absolute value of 8 minus 3 and the absolute value of 3 minus 8. When you're doing the absolute value of a difference, again, the order doesn't matter. The result will still be the same. Let's see how that happens. Start on the inside finding your difference. 8 minus 3 is 5. So we have the absolute value of 5. And again, absolute value is the distance from 0. 5 is 5 places from 0. Now we'll look at the difference switched around. 3 minus 8. 3 minus 8, you could add the inverse of 3 plus a negative 8. 3 plus a negative 8 is negative 5. So we have the absolute value of negative 5. And like we talked about over here, the absolute value of a number and its negative counterpart are the same. So the absolute value of 5 and negative 5 is the same because, again, absolute value is the distance from 0, and distance can never be negative. So the absolute value of negative 5 is also 5, since negative 5 is 5 places from 0. Adding and subtracting decimals. When adding and subtracting decimals, first, line up the decimals. We have 4 and 23 hundredths plus 9 and 75 thousandths. Same with subtraction. 5 and 629 thousandths minus 45 hundredths. Then if you have any empty spaces, you can fill in with zeros. Adding zeros to the back of your number to the back of a decimal doesn't change the value of your number. So these numbers are still what they were. They're still equal. And then we just add or subtract like we usually would. 0 plus 5 is 5. 3 plus 7 is 10. So write your 0, carry your 1. 1 plus 2 is 3, plus 0 is 3. Bring that decimal down. 4 plus 9 is 13. So our answer, or our sum, is 13 and 305 thousandths. Now for subtraction. We're going to do the same thing, except now we're subtracting. 9 minus 0 is 9. 2 minus 5. We can't take 5 from 2, so we need to borrow from our 6, just like we usually would, and add a 1 onto our 2, which makes 12. 12 minus 5 is 7. And then 5 minus 4 is 1. We bring our decimal down. And 5 minus 0 is 5. So our result, or our difference, is 5 and 179 thousandths. Adding and subtracting fractions. To add and subtract fractions, first make sure that the denominators are the same. If they aren't, like in 5/9 minus 1/6, then we need to find the least common denominator. The least common multiple of 9 and 6 can be found by listing the multiples 9, 18, 27, etc. 6, 12, 18. Our least common multiple is 18, so we're going to change both of our fractions, 5/9 to something over 18, and 1/6 to something over 18. 9 times 2 is 18. So since we multiplied our denominator times 2, we must also multiply our numerator times 2. 5 times 2 is 10. 6 times 3 is 18. So we must also multiply our numerator times 3, and we get 3/18. So that means that 5/9 minus 1/6 is equal to 10/18 minus 3/18. Now we just subtract our numerators and put that difference over our denominator of 18. 10 minus 3 is 7. Then, if you can simplify the result, you should. But in this case, 7/18 cannot be simplified, so that's our answer. Let's look at an addition problem. Again, we've got to see if our denominators are the same, and if they aren't, then we need to change them so that they are. So we're going to find the least common denominator for 3 and 5, which means we're finding the least common multiple for 3 and 5. So I'll list the multiples: 3, 6, 9, 12, 15. And my multiples for 5, 10, 15. So my least common multiple is 15, which means I'm going to change both my denominators to something over 15. 2/3 equals something over 15. And 4/5 equals something over 15. So to get from 3 to 15, we have to multiply times 5. So we need to do the same to our numerator. 2 times 5 is 10. 5 to 15, we have to multiply 5 times 3. So we do the same to our numerator. 4 times 3 is 12, which means that 2/3 plus 4/5 is the same as 10/15 plus 12/15. And again, we add the numerators and put that result over our denominator. 10 plus 12 is 22. And this is an improper fraction since our numerator is larger than our denominator, so we'd want to change it to a mixed number. To change this improper fraction to a mixed number, we're going to divide our numerator by our denominator. 22 divided by 15 is 1, since 15 goes into 22 one time, with 7 left over out of, and the denominator stays the same. So 1 and 7/15 is our result.
Up here on the board, we have a sequence of numbers of 43, 31, 19, and 7. But notice after this comma, we have dot, dot, and dot, meaning there's more numbers after it. And so if we were going to continue this string of numbers, then we are going to have to figure out what the pattern here is with these numbers. So what we're going to do here is we're going to take this second term right here, and we're going to do the second term minus the first term. So the second term is 31 minus the first term, which is 43, which gives us negative 12. Now, if we were to continue that and do the third term minus the second term, then we get 19 minus 31, which again gets us negative 12. So we're realizing here that each successive number is 12 less than the one before it. So by looking at this, we can come up with an equation to represent this. And so this is the equation we've come up with. And because right here we start with 43, which is the first term we have. So we have n right here. So this represents how many numbers you are into the sequence. So say we're the first number into the sequence, it'd be 1 minus 1 equals 0 times negative 12 is 0. So we get 43. If this was the second term into the sequence, we'd have a 2 right here. So 2 minus 1 is 1 times negative 12 is negative 12 plus 43 is 31. So you can see how this equation works. But I'm going to quickly simplify this for us to make it easier. And so the way this was simplified is we just multiplied negative 12 times n by negative 1 and then added some numbers together. And so we got that right there, the simplified equation. So we're going to take this simplified equation right here, and we can use this to determine what number is going to come later in this sequence. So say we want to know what the 8th number in the sequence is. All we have to do is plug in 8 for n right there. So we take negative 12, we multiply it by 8 in parentheses plus 55. And so negative 12 times 8 equals negative 96 plus 55. And so I'll save you the math on that, but that equals negative 41. So the 8th term in the sequence is going to be 81. And you can do that for whatever number you want to put in for n. If you wanted to find the 72nd number in the sequence, you could do that. You could plug it in. Or maybe you just want to find the 5th number in the sequence. You could plug that in. And so you can see how you can take this sequence. You have to discover the pattern. Then you come up with an equation, and it's going to work for whatever number you want to plug in to n.
Associative property. The associative property states that when adding or multiplying a series of numbers, it does not matter how the terms are ordered. Remember that simplifying within the parentheses is the first step using the order of operations. So you can remember the associative property, the rule for the associative property, because the numbers are grouped or associated with one another. Let's look at a couple of examples. A plus B plus C is equal to A plus B plus C. So again, we're going to do what's in the parentheses first. Let's try this with 2 plus 3 plus 4 equals 2 plus 3 plus 4. So again, we're going to follow our order of operations, or PEMDAS. We're going to start by adding 2 plus 3, 5 plus 4 is equal to 2 plus, and again, following order of operations, 3 plus 4, which is 7. 5 plus 4 is 9, and that does equal 2 plus 7, which is also 9. So you can see it doesn't matter which terms we add first. Since we're doing addition, it doesn't matter what we do first. Let's see what happens when we do the multiplication side. So again, I'm going to use 2 times 3 times 4 is equal to 2 times 3 times 4. According to PEMDAS, we have to start inside our parentheses. So that's 2 times 3 times 4 is 12 is equal to, again, starting in our parentheses, 2 times 3 is 6 times 4. 2 times 12 is 24, and that does equal 6 times 4, which is also 24. Like the commutative property, the associative property is only true for addition and multiplication. Let's look what happens when we try to use it on subtraction and division. So if we tried to use the associative property, it would look like A minus B minus C, but again, it's not going to be equal to A minus B minus C. So I'm going to use numbers like 8 minus 4 minus 2 does not equal 8 minus 4 minus 2. Again, using order of operations, 8 minus 4 is 4, minus 2 does not equal 8 minus 4 minus 2 is 2. 4 minus 2 is 2, and that does not equal 8 minus 2, which is 6. As you can see, the associative property does not work on subtraction. Let's use it on division now. So with division, it would look like A divided by B divided by C, again, will not equal A divided by B divided by C. I'm going to use the same numbers we used for subtraction. So 8 divided by 4 divided by 2 does not equal 8 divided by 4 divided by 2. Let's simplify. Order of operations, 8 divided by 4 must be done first. 2 divided by 2 does not equal, again, parentheses first, 8 divided by 4 divided by 2 is 2. 2 divided by 2 is 1, and that does not equal 8 divided by 2, which is 4. And that's the associative property. Calculation of a percentage. Sometimes, instead of being given a percent, you're asked to find the percentage. Here we have two problems we're going to do where we have to find the percentage. The first one says, what percent, so again, we don't know the percent, of 40 is 35. In this case, we can think of a percent as a part divided by a whole. So in this case, our part would be the 35 out of the whole, which would be 40. Then we divide our numerator by our denominator to get our decimal. 35 divided by 40 is 875 thousandths. And then we convert our decimal to a percentage by either multiplying times 100 or moving our decimal 2 places to the right. So that's 87 and 5/10%. So 35 is 87 and 5/10% of 40. The other way to do it is to, again, start by thinking of your percentage as a part out of a whole, so setting up your fraction. In this case, when we do what percent of 25 is 12, our part is 12 and our whole is 25. But remember, a percent is a part out of 100. So if we convert our denominator to something over 100, then we'll know what that part is. So to change our denominator from 25 to 100, we have to multiply times 4, which means we have to do the same to our numerator. So 12 times 4 is 48. So that's 48 out of 100, or 48%. So 12 is 48% of 25. It's not quite half of it, it's not quite 50%, it's 48%. Changing constants in graphs of functions, linear equations. The slope-intercept form of a linear equation is y equals mx plus b, where the constants are the m and the b. The x and the y are the variables. M stands for slope, while the b is the y-intercept. The slope of a linear equation is how steep or flat the graph is, or how steep or flat the line is. So here we have 3 different graphs. The first graph and the last graph have the same slope. The slope is 1, since the coefficient of x is 1. And this is actually the parent function of a linear equation, y equals x. So when your slope is positive, like it is in the first and the last graph, then the line increases from left to right. The second graph, the slope is negative, negative 1/4. So the line is decreasing now from left to right. If the slope is negative, then the line is decreasing from left to right. Positive slope, increasing, negative slope, decreasing. You may also notice that this line is not as steep as the first and the last. The greater the absolute value of the slope, the steeper the line is. The absolute value of this slope, negative 1/4, would be positive 1/4, and a fourth is less than 1, which is why this line is not as steep as these lines are in the first and the last graph. B, again, is the y-intercept, which means that's where your line crosses the y-axis. And this is the y-axis here, x-axis, y-axis, x-axis, y-axis, x-axis. So in the first and second graph, the y-intercept is 0. There is no y-intercept there, which is why it's crossing the y-axis at 0, the origin, for both of these graphs. However, in the third graph, the y-intercept is 2, which is why this graph has been shifted up 2 places to intercept the y-axis at 2. And so that's really what the y-intercept is. It's a vertical shift up or down on the y-axis. So if our y-intercept was -4, then the graph of our line would go right through this point right here at -4. And that's how the slope and y-intercept affect a linear graph. Changing constants in graphs of functions, quadratic equations. The standard form of a quadratic equation is y equals ax squared plus bx plus c. A, b, and c are the constants. So when the constants are changed, the graph changes. With a, the coefficient of the x squared term, when a is positive, the graph is concave up. So that's this first graph and the last graph. They both have positive coefficients. In this case, 1. A is 1 for both of these graphs, and 1 is positive. So both of these parabolas are concave up. When A is negative, the parabola is concave down, like we have here in the second graph. Y equals negative 2x squared, concave down. This first graph is the graph of the parent function. So it's when none of the constants have been changed. A is 1. There is no b constant or c. They're both 0. So this is the parent function before any shifts have happened. The larger that a is, the greater the absolute value of a, the steeper the graph is, the faster it increases or decreases. So in the first and the last graph, it's 1. In this middle graph, the a is negative 2. And you can tell it's skinnier than these two graphs are because 2 is larger than 1, so it's increasing, or actually in this case, decreasing more rapidly. So if A was, say, 1/2 instead of 2, then the graph would be a wider graph or a shallower graph. It wouldn't be increasing or decreasing as rapidly. The C constant shifts the graph vertically, either up or down. So in both the first and the second graph, the C is 0, and our graph passes through the origin in both of those, and actually that's where the vertex is. However, in this last graph, notice there is no x term. In this last graph, our C is 2, and our graph has been shifted up 2, vertically 2. So the C will always be the y-intercept of the quadratic equation, but it won't always be where the vertex is. If there is an x term in there, then that's not going to be where your vertex is. The only reason the vertex is the same as the C is because there is no x term. And that's the same for all of these. The C is 0 for both of these graphs. Notice the vertex is at 0. But that's because neither one of these have an x term either. So when you throw that middle term in there, that x term, then it starts moving the graphs around. However, the C will always be the y-intercept. It just won't always be the vertex as well as the y-intercept. Changing a mixed number to an improper fraction. To change a mixed number to an improper fraction, first multiply the denominator times the whole number and then add the numerator. You'll then place that value over the denominator. Let's look at 2 examples. For 2 3/4, we'll first multiply 4 times 2, our denominator times our whole number, and then add our numerator. That value goes over our denominator, 4. 4 times 2 is 8. 8 plus 3 is 11. So 2 3/4 is 11/4 as an improper fraction. Let's look at one more. 4 2/5. Again, we're going to start by multiplying our denominator times our whole number. 5 times 4. And then adding our numerator, plus 2. And that value goes on top of our denominator, 5. 5 times 4 is 20, plus 2 22/5. Changing a number from standard form to scientific notation. To change a number from standard form to scientific notation, you need to first rewrite the number so that it is between 1 and 10 by moving the decimal to the left or the right. Let's look at 32,581. To write this in scientific notation, the first thing we have to do is take our decimal and move it to the left or to the right so that this number is between 1 and 10. Where's my decimal? It's at the end of my number. So I'm going to have to move it to right between my 3 and my 2 so that my number is now 3 and 2,581 10,000ths. Now we're going to multiply this times 10 raised to, and this power is found by determining how many places we had to move our decimal. We had to move it 1, 2, 3, 4 places, which means we would need to multiply this number times 10 to the 4th power to achieve our original number. So 32,581 is 3 and 2,581 10,000ths times 10 to the 4th power in scientific notation. This same pattern applies when expressing very small numbers in scientific notation. Let's consider the value 65 thousandths. We're going to start again by moving our decimal so that our number is between 1 and 10. So I'm going to have to move it to between my 6 and my 5. So that gives us 6 and 5/10. But right now these numbers aren't equal. Not until we add our times 10 raised to the, now we have to figure out the power. We moved it 2 places to the right. So we'd have to multiply 6 and 5/10 times 10 to the negative 2 power to achieve our original number. 65 thousandths is equal to 6 and 5/10 times 10 to the negative 2. Computation with percentages. In problems involving percentages, it is usually easiest to convert to a fraction or a decimal. Let's look at 2 examples. First, we're going to calculate 40% of 62. Of in math means to multiply. So we're doing 40% times 62. So now we need to convert 40% either to a fraction or to a decimal. I'm going to convert it to a decimal. And to do that, all I have to do is take my decimal and move it 2 places to the left. So 40% as a decimal is 4/10 or 40 hundredths times 62. 4/10 times 62 is 24 and 8/10. So 40% of 62 is 24 and 8/10. You can use mental math to find percentages, and on this one what we could do is find 10% of 62 first and then multiply that times 4, since 10% times 4 would be our 40% of 62. So to find 10% of 62, we would just move the decimal 1 place to the left, so that would be 6 and 2/10. And then we want to do that 4 times, so we just multiply that times 4. So 6 2/10 times 4, which would again give us 24 8/10. And this you could do a little easier in your head. Let's look at one more. Oftentimes, percentages are used to calculate the tip when you go out to eat at a restaurant. So here we're going to calculate a 20% tip on a $28.75 meal. So we want to know what is 20% of $28.75, since that's how much we need to leave them. 20% of how much our total bill was. So again, of is multiplication, and we want to convert our percent to a decimal. So move it 2 places to the left. So we're really doing 2/10 times $28.75. And 2/10 times $28.75 is $5.75. So we would need to leave them a $5.75 tip. What would our total bill be? Well, our total bill would be how much our food costs plus how much we're leaving in a tip. So $28.75 plus $5.75. 5 plus 5 is 10. Write your 0, carry your 1. 7 plus 7 is 14. Plus 1 is 15. Carry your 1. Bring down our decimal. 8 plus 1 is 9. Plus 5 is 14. Write your 4. Carry your 1. 2 plus 1 is 3. So our total bill would be $34.50 with the tip included.
The processes for converting decimal numbers to fractions and percentages are both fairly simple, so I'll demonstrate both on each of these examples here. First, we have 0.35. To convert 0.35 to a fraction, we'll write the 2 digits in here as the numerator, and we'll take a look at the rightmost digit. The rightmost digit is 2 decimal places to the right of the decimal, so we're going to write 2 zeros in the denominator. So we have 35 over 100. And this can be reduced by dividing both the top and the bottom by 5. 35 over 5 is 7. 100 over 5 is 20. So this is equal to 7 over 20. To convert a decimal to a percentage, all we have to do is move the decimal point 2 places to the right. So 0.35 is equal to 35%. In the second example, we have 0.215. Once again, we'll write 215 as our numerator. The rightmost digit is 3 places to the right of the decimal, so we will write 3 zeros in our denominator. 215 over 1,000. We can divide top and bottom by 5, so 215 over 5 is equal to 43, and 1,000 over 5 is equal to 200. So this fraction is the same as 43 over 200. To convert to a percentage, we can just move the decimal point 2 places to the right. So 0.215 is equal to 21.5%. In this final example, we have 0.842. We will once again write these digits as our numerator. The rightmost digit is 3 places to the right of the decimal, so we will once again have 3 zeros in our denominator. 842 over 1,000. We can reduce by dividing top and bottom by 2. 842 over 2 is 421, and 1,000 over 2 is 500. So this fraction reduces to 421 over 500. To convert to a percentage, once again, we'll just move the decimal point 2 places to the right. So 0.842 is equal to 84.2%. The first step in converting a decimal to an improper fraction is to convert the decimal to a mixed number. So we'll convert to mixed numbers first. In this first example, we have 7.6. To convert this to a mixed number, we'll take the whole part, or the part to the left of the decimal, which is a 7, and then we'll take the part to the right of the decimal, which is a 6. Now, we can put the 6 over a power of 10, and there's only one digit to the right of the decimal, so there's only one 0. So we have 7 and 6 over 10. Now we can reduce this fraction by dividing top and bottom by 2. So we have 3 on top and a 5 on the bottom. So this is equivalent to 7 and 3/5. Now to convert this to an improper fraction, we'll multiply the denominator by the whole number and then add the numerator. 5 times 7 is 35, plus 3 is 38. So we have 38 over 5. In this next example, we're going to once again take the whole number part, which is the 5, and then we will put the part to the right of the decimal over a power of 10. 2 places to the right of the decimal, so 2 zeros, 35 over 100. We can reduce this by dividing top and bottom by 5. 35 over 5 is 7. 100 over 5 is 20. So this is equivalent to 5 and 7 over 20. To convert to an improper fraction now, we'll multiply 20 times 5, which is 100, plus 7, which is 107. So we have 107 over 20. In the final example, we'll once again take the whole number part, 3, and then take the part to the right of the decimal, 375 over 3 decimal places, so 3 zeros, 375 over 1,000. Now, we can divide top and bottom here by 125, which leaves us with 3 over 8. So this number is equivalent to 3 and 3/8. Now to convert to an improper fraction, we'll once again multiply 8 times 3, which is 24, plus 3, which is 27. So we have 27 over 8.
Converting improper fractions to mixed numbers. To convert an improper fraction to a mixed number, first we're going to divide our numerator by our denominator. 22 divided by 5 is 4, with a remainder of 2. 4 is our whole number, while 2 is the numerator of our fraction, and the denominator stays the same. So 22/5 as a mixed number is 4 and 2/5. Let's look at one more. Again, to change an improper fraction to a mixed number, we're going to start by dividing our numerator by our denominator. 18 divided by 4 is 4. 4 times 4 is 16, so we have a remainder of 2. 4 goes into 18 4 times with a remainder of 2 out of 4, since our denominator stays the same. This mixed number is special because we can simplify this fraction 2/4, and when you can simplify, you always want to do that. So 4 and 2/4 simplified would be 4 and 1/2. Since the GCF of 2 and 4 is 2, we divide both numerator and denominator by 2. 2 by 2 is 1, and 4 divided by 2 is 2. So 18/4 as a mixed number is 4 and 1/2.
The methods for converting a mixed number to a fraction and a decimal are very different from one another. So I'm going to demonstrate how to convert to a fraction on all 3 of these examples first. Here we have 4 and 2/5. Now to convert this to a fraction, we have to take the denominator and multiply by the whole 5 times 4, and then add the numerator, 2. So we have 5 times 4 is 20, plus 2 is 22. Now we take that, and that's our new numerator, and we retain the same denominator, 5. So this is the fractional form of that mixed number. Moving on to this one, we have 2. We'll multiply it by 7 to get 14, and then we'll add 1 to get 15. And we retain the same denominator once again, 15 over 2. Finally, this one, we have 4 times 3 is 12, and we'll add this 3 to get 15. So we have 15, and once again, retaining the same denominator of 4, we have 15 over 4. The method for converting to a decimal is to take the whole part of the number, in this case 4, add a decimal point, and then take the fractional part, 2/5, and modify this fraction so that it retains its value but has a denominator of 100. To do this, we have to multiply the top and bottom by 20. 20 over 20. 2 times 20 is 40. 5 times 20 is 100. Once we have a denominator of 100, we can take the numerator and put it to the right of the decimal, 40. So this number is 4.40. In this case, we have a 7. Put a decimal point past it, and we have 1/2. To convert 1/2 to a denominator of 100, we multiply by 50 over 50, and we get 50 over 100. We can take this 50 and put it to the right of the decimal. We have 7.50. In the third example, we have a 3, and we have 3/4. To get 3/4 to have a denominator of 100, we multiply by 25 over 25, and we get 75 over 100. So then we can put 75 to the right of the decimal, 3.75.
Converting a percent to a fraction. To convert a percent to a fraction, remove the percent symbol and place the number over 100. Then simplify if possible. Let's look at a few examples. To convert 40% to a fraction, we're going to remove the percent symbol and place that number over 100. And then we simplify. 40 100ths can be simplified because the GCF of 40 and 100 is 20. So we're going to divide our numerator and denominator by that GCF of 20. 40 divided by 20 is 2, and 100 divided by 20 is 5. So 40% as a fraction is 2/5. 25%. Again, we start by removing the percent sign and putting our number over 100. Then we simplify if possible. 2500 simplifies to be 1/4 when you divide the numerator and denominator by the GCF of 25. Let's look at one more. 8%. 8% is 8 out of 100, which then can be simplified by dividing the numerator and the denominator by the GCF of 4. 8 divided by 4 is 2, and 100 divided by 4 is 25. So 8% as a fraction is 2/25. Decimals. Decimals use place value to represent an amount. To read a decimal, like we have here, first read the number to the left as a whole number, followed by and, then read the number to the right of the decimal, followed by the last place value. So this number would be read as 641 and 5,129 10 thousandths. This number could also be represented as a mixed number. 641 and 5,129 10,000ths. Let's look at another decimal. 5 and 8,139 10,000ths. We could write this number as an improper fraction by taking the 5 plus, this would be 8/10ths since it's in the tenths place, plus 1/100ths plus 3,000ths plus 9/10,000ths, which would give us 58,139 10,000ths. So we've seen a decimal in decimal form. We've seen it represented as a mixed number and also as an improper fraction. Distributive property. The distributive property involves multiplying over grouped addition or subtraction terms. It states that you multiply the number outside of the parentheses by each term inside of the parentheses, and then add or subtract as in the original. You can think of distributing as handing out or giving something out. You're giving out the number on the outside of the parentheses to the numbers on the inside of the parentheses. We're going to look at two examples, one with addition and one with subtraction. If we were doing 2 times the quantity 5 plus 3, then we could use the distributive property to simplify this by distributing the 2 to the 5, 2 times 5, plus 2 times 3. Then we would simplify. According to PEMDAS, we need to multiply first. So 2 times 5 is 10, plus 2 times 3 is 6. Finally, we combine 10 plus 6 for 16. Let's look at this subtraction problem. If we wanted to simplify 4 times the quantity 5 minus 2, we would start by multiplying 4 times 5 minus 4 times 2. And then we would simplify. Following the order of operations, we're going to multiply first. 4 times 5 is 20 minus 4 times 2 is 8. And 20 minus 8 is 12. Dividing decimals. To divide decimals, first move the decimal point in the divisor so that it's a whole number. Then move the decimal point in the dividend the same number of places. And finally, move the decimal point up so that you know where it goes in your answer. So this means that now we're dividing 25 into 789 and 5/10. Now we just divide as we would with whole numbers until we get no remainder, or you know it's a repeating decimal. So 25 goes into 78 3 times. 25 times 3 is 75. We subtract and we get 3. Bring down the 9. And 25 goes into 39 1 time. 25 times 1 is 25. We subtract. 9 minus 5 is 4. 3 minus 2 is 1. Then we bring down our 5. 25 goes into 145 5 times. 25 times 5 is 125. Then we subtract. 5 minus 5 is 0. 4 minus 2 is 2. And then we have to add on a 0 so that we can continue. Since our remainder isn't 0, we still have 20 here. We need to add on a 0 to bring down, because we can add as many zeros after our decimal place as we like without changing the number. 25 goes into 200 8 times. 25 times 8 is 200, so that when we subtract, we get a remainder of 0. Now that we've reached a remainder of 0, we're finished dividing, and our result is 31 58/100.
Math, 3rd grade. When dealing with fractions of a whole, realize that there's a numerator and a denominator in every fraction. So the numerator is on top and the denominator is on the bottom. So we have a fraction bar right here. And so first, we need to determine what goes in the denominator. So that's the total of amount of spaces we have on the fraction strip. So we have the fraction strip right here, so we need to count the total amount of spaces. So count with me. 1, 2, 3, 4, 5, 6, 7, 8. So we need to put an 8 in the denominator here. Now when it comes to the numerator, we need to count the shaded spaces. And so notice these spaces right here, they're all shaded. So now we need to count those. 1, 2, 3, 4, 5. So there's 5 shaded spaces. And so the 5 is going to go in the numerator because we have the whole amount right here and then we have part of the whole. So right here we have a pizza. And so let's count the spaces of this pizza. 1, 2, 3, 4, 5, 6, 7, 8. So again, if we're doing a numerator and denominator, we put 8 in the denominator. So now we need to count the shaded regions for the numerator. So there's 1, 2, 3, 4, 5 shaded regions. So here for this pizza, there were 8 total pizzas, so 8 is the whole. And then 5 is how many are still there. So there's 5 pieces of pizza still there. So 5 goes in the numerator. So although you may mostly be dealing with a fraction strip, try to take that idea right there and think about just a pizza and think about, okay, maybe there's 8 or 5 total pieces of pizza and how many have not been eaten yet. And so that's what you're doing when you look at a fraction strip. So remember that the whole goes in the denominator and then the shaded regions go in the numerator.
Graphing solutions to linear inequalities. First, we're going to graph y is greater than 1/3 x plus 2. To graph a linear inequality, we're going to graph the line as if this were an equal sign. And then if it's greater than or less than, it's a dashed line. If it's greater than or equal to, less than or equal to, we use a solid line. So since this is just greater than, we need to use a dashed line. This is in slope-intercept form. Y equals mx plus b. So our slope is 1/3. And our y-intercept is 2. So we're going to start with our y-intercept at 2. And then use our slope to find our next point. Rise 1, run 1, 2, 3. And then we'll draw our dashed line. Connecting our 2 points. The final thing we need to do to graph an inequality is to shade. But where do we shade? One way to figure this out is to pick a point on either side of the line and see if it satisfies your inequality. If it does, then that's the side you shade. If it doesn't, then you shade the opposite side. A good point to use is 0, 0 because it's pretty easy to solve for. So y is 0 greater than, and then again we'd plug in 0 for x, 1/3 times 0 is 0, 0 plus 2 is 2. So is 0 greater than 2? No, it isn't. Which means since 0, 0 does not work, it is not a solution, then this is not the side we shade. So we shade the other side. And really everything above this would be shaded, but I'm not going to color the whole board. So this would be your solution to this inequality. Every point in this shaded region would make this inequality true. However, points on the line would not make the inequality true since its y is greater than, not greater than, or equal to. And that's why this line is dashed, to symbolize that the points that are on this line, the points that lie on this line, do not satisfy this inequality. Now we're going to graph a system of inequalities. The same rules apply, but where you shade is a little bit different. So first we're going to graph y is greater than or equal to 2x plus 3. Since it's greater than or equal to, we use a solid line. And again, it's in slope-intercept form. So our slope here is 2, or 2 over 1, and our y-intercept is 3. So we start with 3, up 1, 2, 3. And then we use our slope, rise 2, run 1. Now we can draw our solid line through these points because again it's a greater than or equal to. And there are a couple of different ways you can do the shading. One thing you could do is start by figuring out where you would shade for this line. So like again you could use that point 0, 0. 2 times 0 is 0, 0 plus 3 is 3. Is 0 greater than or equal to 3? No, it isn't. So for this line, we'd be shading on this side of the line. And we can put it like a little dot here just to remind ourselves. This is the side we'd be shading for this line. And then you can graph your other line and see where you'd shade for that one. Where they overlap is going to be the solution. And that's one way, and I'll show you another way when we're done graphing the other line. So this next line is y is less than negative 1/2 x minus 2. Less than, since it's not less than or equal to, that means we're going to be using a dashed line again. And again, it's in slope-intercept form, so our slope is negative 1/2 and our y-intercept is negative 2. So start with the y-intercept, negative 2, and then use your slope to find your next point. Rise 1, or actually we're going down 1 since it's a negative 1, and then over 2. And again, this is a dashed line because it's just less than, not less than or equal to. We're going to connect our points with our dashed line. And put our arrows on the end to signify that that line goes on. So now that we have our two lines crossing, we've actually created 4 regions. We have this region, this one, and this one. For our first line, this region was what was shaded. So now we need to see where we're shading for our next line. Is it above the line or below this dashed line? Again, I'm just going to use 0, 0 in order to check. So negative 1/2 times 0 is 0. 0 minus 2 is negative 2. So is 0 less than negative 2? It is not. So this is not where we're shading for this one. We're shading down here in this region. And so where the two shaded areas overlap would be right over here. This is your solution, since for this line we were shading on this side, and for this line we were shading on this side. So the two shaded areas that overlap is just this region right here. And another way you could figure this out is just to pick a point in all four of the regions. And if the point satisfies both equations, then that's where you shade. And if your point doesn't satisfy both equations, then we don't shade in that region. Graphing the inverse of a function. The inverse of a function is the same as the original function, but with the independent and dependent variables switched, which just means switch the x and y values in the coordinates. The inverse of a function and the original will look the same, except that again, those x and y values will be switched, which means that they will be symmetric, the two graphs will be symmetric about the line y equals x. Let's look at an example. Graph y equals 2x plus 3 and the inverse. Y equals 2x plus 3 is a linear equation, and it's in slope-intercept form. Y equals mx plus b. The m is our slope, so our slope is 2, or 2 over 1. And our y-intercept is 3. B is 3. To graph a linear equation, we start by graphing the y-intercept. So on our y-axis, we go up to 3, and there's the first point for our line. The slope is our rise and our run. So we need to rise 2 and run 1 from that point. Rise 2, run 1. Now we just need to connect those points with a line. And then put arrows on the end of our line to signify that that line goes on forever. So that's the graph of our original function, but how about the inverse? Remember from just a minute ago that the inverse of a function is just where the independent and dependent variables are switched. The independent variable being the x and the dependent being the y. So one way we could graph our inverse function is just to take our x and y coordinates from each one of these points and switch them. So this ordered pair is 0, 3. Which means that our inverse function will have the ordered pair 3, 0. Just switch the x and y. So over 3 and then up 0. There's the first point for our inverse function. Then we can take this other point we put on our graph, which is 1, 5, and do the same thing. Just switch the x and y coordinates, which makes it 5, 1. So over 5 and up 1. We could have done this with any 2 points from our original function, but since these were the 2 points we used to graph our line, they were easy to use to switch the x and y coordinates. Now that we have our 2 points for our inverse function, we can connect those with a line. And put arrows on the end to signify that it goes on and on and on forever. Now that's one way to graph an inverse function, to graph the original and then take the ordered pairs from the original and switch them. The other way to graph an inverse function, or another way to graph an inverse function, is to take the original function and again switch the x and y. So the y becomes x and the x becomes y. Now if we wanted to graph this, we'd want to put it in a form like slope-intercept form, which means we must solve for y now. So start by subtracting 3 from both sides. X minus 3 is equal to 2y, plus 3 minus 3 are additive inverses, so they cancel. And then we divide both sides by 2 to solve for y. 2 divided by 2 is 1, and 1 times y is y. I'm going to use the symmetric property to flip this around, so I get y equals x minus 3 divided by 2. Or y equals x divided by 2 minus 3 halves, or y equals 1/2 x minus 3 halves. You can write it in lots of different ways. But then you could graph this inverse function the same way we graphed our original function by graphing the y-intercept, -1.5, and mine's a little off because of human error, but it should be about right there. And then we would use our slope 1/2 to rise 1 and run 2. So when you're graphing a function and its inverse, just remember, switch the x and y. Graphs of functions. The first graph is a linear function. It graphs a line. The second graph is what's called a quadratic function. Quadratic functions graph a u or a parabola. The third graph is an exponential function. Exponential functions start out increasing very slowly and then start increasing more and more rapidly. This next graph is the graph of a logarithmic function. A logarithmic function is the inverse of an exponential function. We should also talk about the asymptotes of an exponential and a logarithmic function. An exponential function has a horizontal asymptote of y equals 0. While a logarithmic function, since it's the inverse of an exponential function, has a vertical asymptote of x equals 0. And an asymptote is just a line that the graph is approaching but doesn't cross. The next graph is what's called an absolute value function. And it graphs a V. It looks like a V. So they're straight lines, and then the left side is just the reflection of the right side. This next graph is the graph of a square root function. And a square root function is a parabola turned on its side, and it's just the top half of the parabola turned on its side. And then the last function is the graph, this is the graph of a rational function. And rational functions have two branches, one in the first quadrant and one in the third quadrant. If you look at this branch here, as we move from left to right, it's decreasing. And the same with the other branch, as we move from left to right, it decreases. And so there are some of the basic functions and their graphs. Greatest common factor. The greatest common factor, or GCF, of two numbers is the largest value that divides into each of the numbers. Let's take, for instance, 18 and 30. You can find the GCF of two numbers by finding the prime factorization of your numbers and then finding what they have in common. So the prime factorization of 18 is even, so it's divisible by 2. So 2 times 9 would be 18. 9 is not prime though, so we need to break 9 down. And the factors of 9 are 3 times 3. So the prime factorization of 18 would be 2 times 3 times 3. 3 times 3 is 9, times 2 is 18. I always like to check after I've factored to make sure I've got it. The prime factorization of 30. 30 is divisible by 2 also, since it's even. So 2 times 15 would be 30, but 15 is not prime. So we have to break it down into its prime factors. And 15's prime factors are 3 times 5. So the prime factorization of 30 is 2 times 3 times 5. 2 times 3 is 6, and 6 times 5 is 30. Now again, to find the GCF, we're going to look for what they have in common. 18 and 30 have 2 and 3 in common as prime factors. So we take those factors they have in common and multiply them. 2 times 3 is 6, so the GCF of 18 and 30 is 6. 6 is the largest factor that these numbers have in common. Least common multiple. The least common multiple, or LCM, of two numbers is the smallest value divisible by both the numbers, or it's the smallest number that both of your numbers divide into evenly. The LCM can be found by finding the GCF, or greatest common factors, and the remaining factors. The LCM is the product of the GCF and those remaining factors. For example, if we wanted to find the LCM of 18 and 30, we would first need to factor them. 18 is 2 times 9. Since 9 is not prime, we would factor 9 to 3 times 3. 30 is also even, so we'll start with 2. 30 is 2 times 15. 15 is not prime, so we factor 15. 15 is 3 times 5. The GCF, or greatest common factor, is 2 times 3, or 6. So our least common multiple is the product of our GCF, 6, and the remaining factors. The remaining factors are 3 and 5. So 6 times 3 times 5. 6 times 5 is 30. 30 times 3 is 90. So the smallest number that 18 and 30 will both divide into evenly is 90. Linear equations. Marielle has 10 coins in her pocket. All of them are quarters and dimes, and their total value is $1.60. How many of each type of coin does she have? We can solve this by using a system of equations. We're told that she has 10 coins in her pocket and that they're all quarters and dimes. So if we use D for the number of dimes and Q for the number of quarters, then one of our equations could be her number of dimes plus her number of quarters is 10 total coins. Next, we're told that the total value is $1.60. Well, dimes are worth 10 cents. So 10 times however many dimes she has, plus quarters are worth 25 cents, so 25 times however many quarters she has will give us a total of 160. We've eliminated the decimals, so we just move the decimal over 2 times to the right for all of our numbers. So instead of 10 cents, we have 10. Instead of 25 cents, we have 25. And instead of $1.60, we have 160. But you could leave the decimals in there if you wanted to. Now to solve this system, we've got 3 options. We could graph both of these and see where they intersect. We could use substitution or elimination. And it's your choice. For this particular problem, I'm going to use substitution. So I'm going to solve for D in my first equation so I can substitute it in my second equation. So D is equal to, and I have to subtract Q from both sides, so negative Q plus 10. To solve for D, subtract Q from both sides, and you get negative Q plus 10. So in my second equation, I'm going to use negative Q plus 10 to substitute for D. So we have 10 times the quantity instead of D, negative Q plus 10, plus 25Q is equal to 160. Now we can solve for Q. To do that, first we need to distribute. 10 times negative Q is negative 10Q. 10 times 10 is 100, so plus 100, plus 25Q equals 160. Now to solve for Q, we need to combine like terms. Negative 10Q plus 25Q is 15Q, plus 100 is equal to 160. Subtract 100 from both sides, and we get that 15Q is equal to 60. Now we divide both sides by 15. 15 divided by 15 is 1, and 1 times Q is just Q. We get that Q is 4, which means she has 4 quarters. So how many dimes does she have? Well, we know that her number of dimes is equal to negative Q, so negative 4, plus 10. So her number of dimes is negative 4 plus 10, 6. So we can say Marielle has 4 quarters and 6 dimes in her pocket. Measurements for similar triangles, example 1. Triangle ABC is similar to triangle EDF. If the length of AB is 9 inches, the length of BC is 8 inches, the length of EF is 9 inches, and the length of DF is 12 inches, what are the lengths of AC and DE? Since we're told that these triangles are similar, that means that the ratios of the corresponding sides are equal. Corresponding means that those sides are in the same place in the similar triangles. And since the ratios of the corresponding sides are equal, that means we can set up a proportion to solve for the missing sides. We'll start by setting up the ratio of the only pair of corresponding sides we know, which is BC to DF. We don't have CA, so we can't use these two sides as a ratio, and we don't know DE, so we can't use these corresponding sides as a ratio. So you start with 8 to 12, and that's equal to If we wanted to find AC first, AC, the length of AC and then the corresponding side there would be 9. And the key with proportions is to be consistent. So since we set up our first ratio as ABC to triangle EDF, then the second ratio had to be set up the same way with a length from triangle ABC on top and then the corresponding length from triangle EDF on the bottom. To solve proportions, we cross multiply. So 12 times AC is 12 AC is equal to 8 times 9, which is 72. Then to solve for AC, we just need to divide both sides by 12. 12 times AC, and the opposite of that is dividing by 12. 12 divided by 12 is 1, and the length of AC is 6 inches. And we can do the same to find our other length that's missing, the length of DE. So again, we can set up a proportion using those two corresponding sides we know, so 8 to 12 is equal to, since we want to find the length of DE, AB corresponds to that. They're in the same spot. So the length of AB, which is 9, goes on top, and then the length of ED is the denominator. And to solve a proportion, we cross multiply. 8 times ED is 8 ED is equal to 9 times 12. 9 times 10 is 90. 9 times 2 is 18. 90 plus 18 is 108. And then to solve for the length of ED, we need to divide both sides by 8. Divided by 8 and divided by 8. 8 divided by 8 is 1. And the length of ED is 13 5/10 inches. Multiplying decimals. When multiplying decimals, instead of lining up the decimal point, we line up the last digits on the right. So if we were multiplying 4 23/100 times 9 75,000, we'd want to line up our last digits. So 3 is the last digit in 4 23/100, and 5 is the last digit in 9 75,000. There's my 7, my 0, my decimal, and 9. Now we multiply just like we multiply whole numbers. So starting with 5, 5 times 3 is 15, carry the 1. 5 times 2 is 10, plus 1 is 11, carry the 1. 5 times 4 is 20, plus 1 is 21. And then I'll get rid of these. For our next number, now that we're multiplying times the 7, we need a 0 placeholder. 7 times 3 is 21. Write your 1, carry your 2. 7 times 2 is 14, plus 2 is 16. Write your 6, carry your 1. 7 times 4 is 28, plus 1 is 29. Get rid of those. Then we need 2 zeros for placeholders. And when we multiply times 0, 0 times 3 is 0, 0 times 2 is 0, and 0 times 4 is 0. We just get a line of zeros. So moving on to our last digit, now we need 3 0 placeholders before we multiply times 9. 9 times 3 is 27. Write the 7, carry the 2. 9 times 2 is 18, plus 2 is 20. Write the 0, carry the 2. 9 times 4 is 36, plus 2 is 38. Then just like we would with any other whole numbers, we're going to add our results together. 5 plus all these zeros gives us 5. 1 plus 1 is 2. 1 plus 6 is 7. 2 plus 9 is 11. Plus 7 is 18. Write our 8. Carry our 1. 1 plus 2 is 3. And then we have 8 and our 3. To determine where the decimal point goes when you've multiplied your decimals together, we're going to take how many numbers there were behind our decimal in our first number and how many numbers there were behind our decimal in our second number and add those together. So since we had 2 numbers behind the decimal here and 3 numbers behind the decimal here, then our result will have 5 numbers behind the decimal. 2 plus 3 is 5. 1, 2, 3, 4, 5. So this is the result of multiplying my 2 decimals together. Ordering decimals. When ordering decimals, place value is very important. We're going to begin by looking at the numbers to the left of the decimal. So if we look at our numbers, to the left of the decimal, if we're ordering these numbers from least to greatest, then the smallest number to the left of our decimal is this whole number, -3. -3 is the smallest whole number out of our whole set. So -3 and 68 hundredths would be our first decimal, least to greatest. So we're going to look for our next biggest, which means we're still looking at our whole numbers. So again, looking at our whole numbers, the next whole number, the next biggest, would be 56 thousandths, because the whole number 0 is greater than -3, but it's smaller than these whole numbers 2 and 3. So our next number would be 56 thousandths. So again, we're going to look for the next greatest whole number. So looking at our whole numbers again, 3, 3, 2, and 2, 2 is going to be our next number. 2 is smaller than 3. But we have 2 of them. We have 2 numbers with the whole number 2 in front. So we've got to move to our next place, our 10ths place, and look at the 10ths place to see which of our numbers would be the next in our line from least to greatest. So looking at the 10ths place, this number, 2 and 2,344 10,000ths, has a smaller number in the 10ths place than our other decimal does. So since we're ordering from least to greatest, this number would be next. Followed by 2 and 3,872 10,000ths, since it was the next because of our whole numbers. So we're done with our 2's, moving on to our next whole number. These 2 are the last ones I have, and again, they have that same whole number. So then we'd move to the 10ths place to compare our 10ths place and see which one is smaller. Looking at our 10ths place, again, they have the same number. So still we don't know which one's going to come next. So we move on then and look at the 100ths place. Looking at the 100ths place, they're still the same. So right now we still can't tell which one's bigger, which one's smaller. So we move one more place over to the 1000ths place. Looking at the 1000ths place for this number, we have a 2 in the 1000ths place. But looking at 3 and 57 hundredths, there is no number in the 1000ths place. When you're missing a number after your decimal, it's always 0. In fact, you could fill in as many zeros after each one of these numbers as you wanted to. It doesn't change your number. So since this number has a 0 in the 1000ths place and this decimal has a 2 in the thousandths place, that means this number is smaller, so it'd be our next number in the series. So 3 and 57 hundredths, followed finally by 3 and 572 thousandths. So when you're ordering decimals, start by looking at your whole number and ordering that from least to greatest. If your whole numbers are the same, like they were here, then look at the tenths place and see which one is smaller in your tenths place. If, like in these numbers, you have the same whole number, the same number in the tenths place, then you move to the hundredths. If those are the same, you move to the thousandths, and so on until you find the numbers from least to greatest. Ordering fractions. When ordering fractions, you must first look at the denominator. If the denominators of the fractions are the same, then you order them according to the numerators, with the values increasing left to right. Let's look at an example. You can see all the denominators are the same. So we're going to order these fractions by looking at our numerators. If we're ordering them from left to right, or from least to greatest, then the smallest number would be our biggest negative number, -7/9. Our next number would be our next negative number, -4/9. Next biggest would be our first positive number, 2/9. And finally, 4/9. Now let's look at some fractions that don't have the same denominator. For these fractions, we could first find the least common denominator, so that we could have all the same denominator and then order them by the numerator. The least common denominator, or LCD, for 4, 12, 2, and 6 would be 12. So first, we're going to convert all these fractions to have the denominator of 12. 3/4. To convert 3/4 to something over 12, we'd need to multiply 4 times 3. So we'll do the same to our numerator. 3 times 3 is 9, and 4 times 3 is 12. So 3/4 is 9/12. -7/12 already has our least common denominator of 12, so we're going to leave it alone. 1/2, 2 would need to be multiplied by 6 to get 12, so we'll do the same to our numerator. 1 times 6 is 6, 2 times 6 is 12. -5/6. 6 would need to be multiplied by 2 to get 12, so we'll do the same to our numerator. 5 times 2 is 10, 6 times 2 is 12, and of course, it's still negative. Now we can order our fractions based on their numerators, from least to greatest, from left to right. Our smallest number is our biggest negative, which is -10/12. Then our next negative, -7/12. Then 6/12. And finally, 9/12 would be our largest number.
Finding percent decrease for a pair of numbers is very similar to finding percent increase, but the formula is a little bit different. Once again, I'll demonstrate on 3 different types of number pairs. First decimals, then fractions, then dollar amounts. In the first example, we have 3.6 and 2.0. To find percent decrease, we'll take the first number, subtract the second number, and divide by the first number. So what we have is 3.6 minus 2.0 over 3.6. We can simplify this by subtracting 2 from 3.6, and we get 1.6 over 3.6. Now if you reduce this fraction, what you wind up with is 4 over 9, whose percentage equivalent is 44.4%. In the second example, we have 5 over 6 and 2 over 3. Once again, we'll take the first number minus the second number over the first number. Now, we don't have a common denominator yet, but we can convert the second number to a denominator of 6, and then we'll have it. So we'll multiply this by 2 over 2, and what we wind up with is 5 over 6 minus 4 over 6, divided by 5 over 6. Now, 5 over 6 minus 4 over 6 is just 1 over 6. So what we have is 1 over 6 divided by 5 over 6, or 1 over 6 times 6 over 5. Now the 6's cancel here, and what we're left with is just 1 over 5. The percentage equivalent for 1 over 5 is 20%. In this final example, we have $230. So we'll take once again the first number minus the second number divided by the first number. Now 200 minus 30 is 170. So what we have is 170 over 200. Now, since our denominator is already so close to 100, we'll just convert it to 100, and then we'll have our percentage figured out already. So we'll divide top and bottom by 2. 170 over 2 is 85, and 200 over 2 is 100. So what we have is 85 over 100, which by definition is 85%. In this example problem, we have 3 different types of number pairs. We have decimals, fractions, and dollar amounts. And what the question asks us to do is to find the percent increase for each of these pairs. Now, the formula for finding the percent increase is going to be the same for all 3 pairs, but the process will be a little bit different depending on the type of number. But I'll demonstrate all 3. The first one, we have 3.0 minus 1.8 divided by 1.8. And the formula is the second minus the first over the first. And that's going to be consistent throughout. Now to solve this, we can take 3 minus 1.8, which is 1.2. So we have 1.2 over 1.8, which is equivalent to 2 over 3. And the percentage form of 2 over 3 is 66.7%. In the second example, we have 1 over 4 and 2 over 5. So we're going to use the same formula as here. We're going to have 2 over 5 minus 1 over 4 divided by 1 over 4. Now we have to get a common denominator here, so we're going to multiply this first number by 4 over 4 to get 8 over 20. And the second number we're going to multiply by 5 over 5 to get 5 over 20. So what we have here is 8 over 20 minus 5 over 20, which is equal to 3 over 20. And then we have to divide it by 1 over 4, or equivalently, what we have here is 3 over 20 times 4 over 1. Now the 4 and the 20 cancel. Dividing each by 4, we get a 1 and a 5. So what we have here is 3 over 5. Now the percentage equivalent of 3 over 5 is 60%. In this final example, we have dollar amounts. We have 225 and 405. So we'll take the final amount, 405, subtract the initial amount, 225, and divide by the initial amount, 225. Now, 405 minus 225 is 180. So what we have is 180 divided by 225. Now we can reduce this by dividing top and bottom by 45. 45 goes into 180 4 times, and 45 goes into 225 5 times. So what we have is 4 over 5, or the percentage equivalent, which is 80%.
Percentages. Percentages are values that are used to compare numbers to 100. All percentages equal the number divided by 100. For example, 35% means 35 out of 100. So you could express it as 35 out of 100, which could then be simplified to 7/20. You could also write 35 out of 100 as a decimal 35/100. So percentages, again, are just that number out of 100. Let's take 85%. 85% means 85 out of 100, which can also be simplified to 17/20. And 85/100 can be written as a decimal 85/100. Prime number. A prime number is a natural number higher than 1 that cannot be divided by any other natural number besides 1 and itself. Here is a list of the first 7 prime numbers. 2 can only be divided by itself and 1. 3 can only be divided evenly by itself and 1. 5, the same. 7, so on and so forth. Notice that in our list of prime numbers, the number 1 is missing. 1 is not considered a prime number since it doesn't have 2 divisors or 2 factors. 1 can only be divided by itself, 1. So to be a prime number, you have to be able to divide it by 2 numbers, 2 and only 2. Like on 2, we can divide it by 2 and by 1, but nothing else will divide 2 evenly. Notice also we're missing the number 4. 4 is not a prime number because it can be divided by 1, 2, and 4. So it can't only be divided by itself and 1. That's the same with 6, 8, 9, 10, etc. Those kinds of numbers are called composite numbers. So prime numbers are numbers that can only be divided by 1 and itself, and composite numbers would be all the other numbers. However, 1 is neither. 1 is neither prime nor composite. It's special. Proportions. A proportion is a ratio equal to a ratio, or a fraction equal to a fraction. You've actually been using proportions for a long time. Anytime you simplify a fraction, like 10/16 is simplified to 5/8, then you've written a proportion because you've written a ratio equal to a ratio. Now in your proportion, you can do what's called the cross products to tell if your ratios are in fact equal. For instance, with this one, 10 times 8 should equal 16 times 5 if these ratios are in fact equal. 10 times 8 is 80, and 16 times 5 is 80. So since the cross products are equal, that means that our ratios are in fact equal. We can also use this cross products principle to solve proportions. For instance, if instead of 10/16 equals 5/8, we had 10/16 equals x over 8, as in we didn't know what our numerator was, then we could use cross products to solve for our variable x. So we would cross multiply. 16 times x is 16x equals 10 times 8 is 80. And then we would solve for x. This is 16 times x, so the opposite of multiplying would be to divide both sides by 16. Then we have 16 divided by 16, which is 1. 1 times x is x. And 80 divided by 16 is 5. So by using the proportion and the cross products, we can find missing values in our proportion, like that x is 5, which we already knew from our original proportion. Proportions and percents. Proportions can be very helpful in solving problems dealing with percents. Let's look at this problem. Suppose a pair of shoes is on sale for 20% off of the original price. If the original price is $85, how much money will you save? Keep in mind that a percent is a part out of a whole. And that whole is 100 when you're dealing with a percent. So 20% off, that would be 20 out of 100. And now we've set up our first ratio. And the key with proportions is to be consistent with your ratios. So since our first ratio is the part out of the whole, then our second ratio also needs to be the part out of the whole. The whole in this case being your price. That's the total cost, so that's your whole. That's your denominator, 85. And then the how much money you save is going to be your part, because you're only going to save part of the whole. And since that's what we're trying to find, how much money will you save, that's going to be our variable. So we can just use an x or anything. And then to solve our proportion, we're going to cross multiply. So we cross multiply 100 times x, which is 100x, is equal to 20 times 85. 2 times 85 is 170, and then we add a 0 for the 20, so 1700. Then to solve for x, we have 100 times x, and the opposite of multiplying is dividing. So we divide both sides by 100. 100 divided by 100 is 1 times x is x. Cancel our two zeros. 17 divided by 1 is 17. Therefore, if our $85 pair of shoes was 20% off, then we'd be saving $17 when we buy our shoes. Proportions in the real world. Proportions can be very helpful in solving many real-world problems. Just be sure that when you set up your proportion, you're consistent in both your ratios. Let's look at this problem. Suppose Hannah makes $10 per hour pulling weeds for a neighbor. How much money would she make if she were to work for 12 hours? So what we're trying to determine is how much money she would make if she worked in 12 hours. And the information we already have is that she's going to make $10 just by working 1 hour, $10 per hour. So we could set up a proportion with the amount of money she makes divided by the time or the hours spent working. So again, we know that she makes $10 in 1 hour. So as we set up our proportion, again, it's very important to be consistent. So if our first ratio, we're going to put dollars per hour, then our other ratio needs to also be set up as dollars per hour. And since the money is what we don't know, how much money would she earn, we don't know the dollars, so there we can put a variable divided by, and then in 12 hours, so that's our time. So with both ratios, we've put our money divided by the time. Now that we've set up our proportion, we can solve it by using cross products or just by cross multiplying. So we're going to multiply 1 times x, which is just x, equals 10 times 12, 120. Therefore, she would make $120 by working 12 hours. Rates and unit rates. Ratios are considered rates when they compare two different units, like miles per hour or cost per ounce. A unit rate is one in which the numerator of the fraction is compared to a denominator of 1 unit. That way you can tell, for instance, like how much just 1 ounce of something costs. And you'll see unit rates a lot at the grocery store under or next to the price of an item. It'll tell you how much that item costs for every 1 ounce or for every one thing in the package. So let's look at a problem dealing with rates and unit rates. Dave is driving 240 miles to his aunt and uncle's house. If he gets there in 4 hours, how many, and here's the key right here in the question, how many miles per hour did he drive on average? In that question, they're telling you how to set up the problem. They're telling you to put miles over hours. So we're going to start with that. Miles per hour. And now we can substitute the information in from the problem. So they told us how many miles. He's going 240 miles. And they told us how many hours. 4 hours. So we can put that into our rate, 240 miles for his 4 hours. So right now this would be considered a rate since we have two different units, our miles and our hours. But to determine our unit rate or to figure out his average, we would need to divide or simplify our rate to find our unit rate. So if we want to have a denominator of 1, then we're going to have to divide 4 by 4 to get our 1. And if we divide our denominator by 4, then we must also divide our numerator by 4. 240 divided by 4 is 60. So again, this is miles per hour. So what this unit rate tells us is that on average, he was going 60 miles for every 1 hour. So your answer could be written as 60 miles per hour is how fast Dave was going on average.
One of the most basic concepts in algebra is the single variable equation. A single variable equation consists of a variable, usually x, and some other numbers. And all you have to do to solve it is isolate x on one side of the equation by performing the same operations to both sides of the equation. So let's look at some examples here. In this first one we have x plus 13 equals 25 minus 19. So to isolate x, we need to get this 13 to the other side of the equation. To do that, we need to subtract 13 from both sides of the equation. So this will cancel, and what we're left with is x equals 25 minus 19 minus 13. And so now all we have to do is solve this part over here, and we've got the value of x. So let's do these one at a time. X equals 25 minus 19 is 6. So x equals 6 minus 13. And 6 minus 13 equals negative 7. So in this equation, x equals negative 7. In the second example, we have 10 minus x plus 38 equals 54 minus 17. Now, in this equation, we have a negative x. So the first thing we want to do is get x to be positive. So to do that, we can add x to both sides of the equation. And that'll give us 10 plus 38 equals 54 minus 17 plus x. Okay, the next step is going to be to move these numbers over to this side so that x is over there by itself. So we need to subtract 54 from both sides and add 17. So what we have now is x equals 10 plus 38 minus 54 plus 17. And so once again, we'll just do these one at a time. 10 plus 38 is 48. 48 minus 54 is negative 6. And negative 6 plus 17 is 11. So in this equation, x equals 11. When you're faced with a complex single variable equation like this one, the first thing you want to do is remove the fractions from this by multiplying both sides of the equation by the product of the two denominators. So we're going to multiply the left and right sides of the equation by 3 times x. So if we multiply this side by 3 times x, what we get is we can cancel out this x, and what we're left with is 3 times 3x plus 17 minus 11. If we multiply the right side of the equation by 3x, we can cancel out the 3, and what we're left with is 10x. So now we just have to solve this for x. This 3 gets distributed to each of these terms, so 3 times 3x is 9x, plus 3 times 17 is 51, minus 3 times 11 is 33, equals 10x. Now, the next thing we want to do is get x all by itself on one side of the equation. So we're going to subtract 9x from both sides, and that'll cancel this out, and that'll leave us with just x over here. And we still have the 51 minus 33. Now to solve for x, all we have to do is subtract 33 from 51, and the solution to that is going to be 18. So that is how you solve an equation like that. To solve a single variable equation, all you have to do is isolate x on one side of the equation and move everything else to the other side. And you do that by performing the same operations on each side of the equals sign. In this example here, we're going to have to use multiplication and division to isolate x. So the first thing we want to do in solving this problem is to rewrite it in a simplified form. Because what we have is 3x times 12 divided by 5 equals 2x times 15x divided by 20. So let's simplify this a little bit. We have 3x times 12, which is 36x, divided by 5, and that's equal to 2x times 15x, which is 30x, divided by 20. 30x squared. So the first thing we want to do is get x all by itself on one side. So we'll divide both sides of the equal sign by x, and that gives us 36 over 5 equals 30x over 20. Now the next thing to notice is that you can reduce this fraction from 30 over 20 to 3 over 2. So we have 36 over 5 equals 3 over 2x. And now what we want to do is get this all by itself over here. So we need to move the 3 over 2 onto this side of the equation. And to do that, we're going to multiply both sides by 2 over 3. So 3 over 2x times 2 over 3. The 2's are going to cancel and the 3's are going to cancel, leaving us with x. On this side, when we multiply by 2 over 3, we see that we can cancel the 3 here. So 3 over 3 is 1. 36 over 3 is 12. So what this leaves us with is 24 over 5. So x equals 24 over 5 is our solution. If we want to write this as a mixed number, we can say that x equals 4 and 4/5, or 4.8 as a decimal. If you have an equation where the variable you're solving for is inside of an absolute value, you're going to end up with two solutions. One, assuming that the value inside the absolute value is positive, and one assuming that it's negative. So let's take a look at an example here. Here we've got 2x minus 5 inside of absolute value brackets. So what we want to do is we want to solve this to isolate the absolute value on one side, and then solve the equation for x twice, once assuming a positive value, once assuming a negative value inside of here. So let's do that. We'll multiply both sides of the equation by 3 to get rid of this denominator. So multiply by 3 over here cancels the 3's. Multiplying by 3 over here gives us 9x plus 162. And over here we have our 2x minus 5 in the absolute value. So now that we've got this isolated, we need to solve this equation for x twice, assuming once that this is positive and once that it's negative. So to assume that this is positive, all we have to do is take off these brackets and just solve the equation like this. So we'll subtract 9x from both sides and add 5 to both sides. And that gives us negative 7x equals 167. And this is solved as x equals negative 167 over 7. Now, we also have to solve for the case where this absolute value is negative. So to do that, what we're going to do is we'll take what was inside the brackets and make a negative by adding a negative sign in front of the brackets. And so now we'll solve this equation for x. So if you distribute this negative sign through, what we have is negative 2x plus 5. So what we're going to do is subtract 9x from both sides and subtract 5 from both sides. So what that gives us is negative 11x equals 157. So if we solve this now, what we get is x equals negative 157 over 11. Here we're going to look at a slightly more complex inequality. Now recall, the rules for solving an inequality are very similar to the rules for solving an equation. You can manipulate the inequality by performing operations so long as you perform the same operations to both sides of the inequality. There is, however, one additional provision for inequalities. If you multiply or divide both sides of the inequality by a negative number, you have to reverse the sign on the inequality. So for instance, if I were to multiply both sides of this inequality by negative 1, I would have to change this less than sign to a greater than sign. So let's keep that in mind as we solve this. Now the first thing we want to do here is eliminate the denominator on this fraction so that we can just have whole numbers and whole number coefficients. So what we're going to do is simplify the denominator and then multiply everything through by the denominator. So what we have here is 8 minus 12, which is equivalent to negative 4. So we need to multiply each term in this inequality by negative 4. Now we can multiply, if we multiply this fraction by negative 4, we just eliminate the denominator. So what we're left with is 5x plus 2. Multiply 3x by negative 4 and we get negative 12x. So minus 12x. And we multiply 10x by negative 4 and we get negative 40x. We multiply -1 by -4, and we get a +4. Now note that we multiplied by a negative number, so we have to reverse the sign on the inequality. So this is now going to become a greater than sign. Now all we have to do is isolate the x on one side of the equation and solve for it. So we need to add 40x to both sides. And that'll eliminate x from the right side. And we'll subtract 2 from both sides. So that will get rid of the 2's and get rid of the 40x's. So now we just need to combine our x's. We have 5 minus 12 plus 40, which is going to be 33x, which is greater than 4 minus 2 is 2. So we know that x is greater than 2 over 33. And so that is going to be our solution to this inequality. But let's make sure by plugging back in a value for x that is greater than 2 over 33, just to make sure that this inequality is correct. So 1 is greater than 2 over 33, so we'll plug in 1. So what we've got here, if we plug in 1, is we've got 5 plus 2 over 8 minus 12 plus 3 is less than 10 minus 1. And so we'll simplify this. 7 over -4 plus 3 is less than 9. So 7 over -4 is -1 3/4, plus 3 is going to be +1 1/4. So 1 1/4 is less than 9. So this inequality holds correct.
When dealing with probability, we have theoretical probability and experimental probability. So right here we have the data from 3 games of football. And so the quarterback's completed this many passes out of this many passes attempted. But it's also said that there's probability of this quarterback completing 60 passes out of every 100 attempts. So if we're to look at the probability here, so I'll label that as P, the probability of completion, we have to take a look at the theoretical number of completions and put that over the total pass attempts. And so in this case it's 60 over 100, which translates to 64%. So this is the theoretical probability. But right here we have this data right here from 3 games. And so here, if we're to take a look at this probability, we're going to do the same thing. We're going to take the number of completions and put it over the total pass attempts. And so in this case, we have 51 completions over 67 pass attempts, which translates to 0.76, which translates to 76%. So if you notice here, these 2 percentages are a lot different. And that's the difference here between theoretical probability and experimental probability. Theoretical probability is calculated by just looking at the odds of what's going to happen. So somebody could examine this quarterback's throwing ability, look at his opponents, and say, okay, the theoretical probability here is that he'll complete 60% of his passes. But then when it's all said and done, we have experimental probability, which is what he actually did, which is a 76% chance. Another example of this would be, say, rolling a die, for example. So say you're looking at flipping a coin. And so the probability of landing on heads when flipping a coin is 1/2. So say you flip a coin 6 times. And so 4 times it lands on heads, and twice it lands on tails. And so really, these should be even. Really, for there to be a 50% chance of landing on heads, then you should have landed on heads 3 times, and the coin should have landed on tails 3 times. So this is, right here, the theoretical probability. Because when you flip a coin, there's a 50-50 chance of what it'll land on. There's a 50% chance it'll land on heads and a 50% chance it lands on tails. So if you were to flip a coin 6 times, the theoretical probability is that it would land on heads 3 times and tails on 3 times. But right here we have the experimental probability, and this is what actually happened. So that's the difference between theoretical and experimental probability. Many times you can use a graph to represent data in a more organized way and in a more visual way. So say we have the equation y equals 2x minus 3. What we can do is plug in a couple of numbers for x and then find out what number we get for y. And then we can come up with some coordinates, plug them in here, and then draw a line representing the values of this equation. So we're going to start out by plugging in 0 for x. So I'm just going to put parentheses like that. So 2 times 0 is 0, minus 3 equals negative 3. So y equals negative 3. So the first coordinate we get is x equals 0 and y equals negative 3. Now we're going to plug in 5 for x. So we're going to put 5 in parentheses. So we get 10 minus 3 equals 7. So y equals 7. So in this case, x equaled 5 and y equals 7. So now we have these two coordinates, and we can just plug these in to this graph right here, and we can get a line. And so we have these dash marks here, so I need to go ahead and label these. So we have this x-axis, which runs horizontal, left to right, and then we have the y-axis, which runs vertical, or up and down. So on the right side of the y-axis, the x-axis is positive. And on the left side, it is negative. This works similarly for the y-axis. Above the x-axis, it's positive, and below, it's negative. So first, we're going to take a look at this coordinate right here. So we have the x-coordinate and the y-coordinate. So we find x first, which is 0. So we're right here. Then we go down to negative 3 and draw a dot. And I'm going to go ahead and put the coordinates right there. Then we look for the x-coordinate first and then the y-coordinate. So we find 5. Then we need to go all the way up to 7. So we're going to need to extend this line a little bit to make it up there. And so we're going to go from 5 all the way up to 7 and draw a dot. And then we just need to draw a line all the way up there. And so if you're using a piece of paper, you can often use a ruler. So I'm just going to attempt to freehand this, which means the line is not going to be very straight, as you can see. But we do need to draw the write the coordinates for that too. And so then we have a line. And so you can go all the way up this line and see different points on it. So you can go, oh, okay, if x equals this certain number, then y is going to equal this certain number, because you can follow it across here. You can go down and find the x-coordinate and then go across and find the y-coordinate to figure out some other coordinates here, to figure out some other values for x and y. And so here you just have coordinates written on a page. And so it may not mean much to you. It's hard to visualize what that looks like. But here you have a real visual format, a real organized way to view a lot of data and to be able to keep it and comprehend it.
Word problems and addition. Solving word problems is made easier if you know what certain words mean. For instance, here we have a list of words that all indicate addition. So if when you're reading a word problem, you see more than, increased by, some, total, or in all, then chances are you're going to be adding something together. Let's look at an example. 2 more than a number is 15. What is the number? The first thing I'm going to do is translate these words into a mathematical sentence. So 2, I'm going to write the number 2 More than, I know, tells me to add. When it says a number, well, that's something I don't know. What number is it? And so if it's something I don't know, then I can put a variable there, like an x or a y, or really anything you want to use. Is in math means equals, and then equals 15. So the only kind of trick here is that more than tells you to reverse the order. It's not just addition. It means instead of doing 2 plus x, I'm really doing x plus 2 equals 15. So now you can probably just look at this and see what number you would have to add to get 15. And that number would be 13, which means x is 13. If you don't know by looking at it what the answer is, then you can solve it algebraically here by subtracting 2 from both sides. But again, you would get that your number is 13. Word problems and division. Here we have a list of some words that indicate division. So if you're trying to solve a word problem and you come across the word quotient, per, out of, or ratio, you'll know that you need to divide something. Let's look at an example. If the quotient, there's one of our key words, of a number and 10 is 3/5, what is the number? So again, we saw that keyword quotient, which tells us we're going to be dividing something. We're going to be dividing two numbers. And those numbers we're dividing are a number and 10. And they must be divided in that order. So when we write our division problem, we could write it as x divided by 10, or we could write it as x divided by 10. But it must be in that order. If we reverse it to do 10 divided by x, then that is not what is written here in this problem. That would be if the quotient of 10 and a number. So order is very important. Since it was written if the quotient of a number and 10, then we must have that number first divided by 10. And you'll see here that I put x, and I put an x because we don't know that number. It just said a number. So when we don't know a number, we use a variable in place of that. Let's finish the sentence. If the quotient of a number and 10 is 3/5, is equals 3/5. Now, since I chose to write it this way, x divided by 10 equals 3 divided by 5, it looks like a proportion, and that's because it is one. All a proportion is a ratio equal to a ratio, and that's what I have here. So to solve this proportion, we're going to cross multiply. X times 5 is 5x, and that's equal to 3 times 10, which is 30. And now we need to solve for x. This is 5 times x, and the opposite of multiplying is dividing. So we divide both sides by 5. 5 divided by 5 is 1. 1 times x is x, and that equals 30 divided by 5, which is 6. So the quotient of 6 and 10 is 3/5. And that's true. 6/10 does simplify to be 3/5. Word problems and multiplication. When you come across a word problem that has any of these words, product, times, twice, or of, chances are you're going to have to multiply. Now this is not a comprehensive list of all of the words that would tell you to multiply, but this is a few of them. Let's look at an example. If Marianne opens a bank account with $450 and earns 12% in interest each month, what will her total balance be at the end of the first month? So what they're asking us to find is our total balance. Since I don't know the total balance, then I'm going to have to use a variable for that. So let's say T then is going to be our total balance. And in order to find my total balance, I'm going to have to take what she's starting out with, her $450, and the amount that she earns in interest in that month. So my total balance will be found by taking the starting value and adding the interest to find my total balance. So to find my total balance, I'm going to have to know the starting value. So we'll use an S for starting value, which is $450. And I also have to know my interest. So we'll use I for interest. And interest is going to be found by doing 12% of the amount of money she has in her account. So we're going to do 12% of $450. Okay, so to find my total balance, I'm going to have to take my starting value and add my interest to that. And my starting value is $450. So my total balance is going to be $450 plus my interest. And my interest, we said, was 12% of $450. And there's one of those words that means multiplication. So in order to find my interest, I'm going to have to do 12% times 450. But first we're going to change our percent to a decimal. So we move our decimal 2 places to the left. So we get 12 hundredths times 450 as our interest. And 12 hundredths times 450 is 54. So our amount of interest that we earned in that month was $54. Therefore, our total amount is $450 plus $54. And then we just add those two amounts together. Therefore, our total amount is $504. And that's how much money we have after 1 month. Word problems and subtraction. When you read a word problem and you see words like difference, less than, decreased by, or fewer, then you know you're going to need to subtract. Let's look at an example. 6 less than a number is 8. What is the number? Since they're asking us what the number is, that means we don't know it. And if we don't know a number, then we use a variable for it. So right here where we see a number, I'm going to put a variable. I'm going to use x. This phrase less than tells us that we need to subtract. So we have 6. We're subtracting. We've got a number. Is an equal sign 8. But less than is a tricky phrase. It does mean to subtract, but again, you have to reverse the order of the things you're subtracting. Like if I said, I have $5 less than Jimmy has. That means that Jimmy has more money than I do. So I'd have to do Jimmy's money minus $5 in order to find out how much money I had. So 6 less than x is going to be x minus 6 is equal to 8. So what number would I subtract 6 from to get 8? that number is 14. So that means x is 14. Now, if you didn't know that the number was 14, then you could solve this algebraically by adding 6 to both sides. So you'd have, again, x equals 14 because 8 plus 6 is 14. Multiples. You can think of multiples as like counting by that number. So for instance, the multiples of 2 would be 2, 4, 6, 8, 10, etc. The multiples of 3 would be 3, 6, 9, 12, 15, 18, etc. The multiples of 4 would be 4, 8, 12, 16, 20, and so on. Sometimes you're asked to find the LCM of 2 or more numbers. The LCM is the least common multiple. Least meaning the smallest, common meaning the same, and multiple. So if we wanted to find the LCM of, let's say, 2 and 3, the least common multiple of 2 and 3, so the smallest number that 2 and 3 have in common, would be 6. So that's the LCM of 2 and 3. The LCM of, say, 3 and 4, the very smallest number that they have in common would be 12. And you can find the least common multiple of bigger numbers, like, say, the least common multiple of 12 and 15. So 12 would be 12, 24, 36, 48, 60, 72, etc. While 15 would be 15, 30, 45, 60, So if we were finding the LCM of 12 and 15, the smallest number they have in common is 60. So the least common multiple is 60. Multiplying and dividing fractions. To multiply two fractions, simply multiply the numerators and multiply the denominators. 3 times 2 is 6, and 4 times 5 is 20. Then we can simplify. 6 and 20 are both divisible by 2. So divide your numerator by 2 and the denominator by 2. 6 divided by 2 is 3, and 20 divided by 2 is 10. So 3/4 times 2/5 is 3/10. Now there is somewhat of a trick or a shortcut when multiplying fractions, so I'll show you that. 3/4 times 2/5. When you're multiplying fractions, before you multiply, look and see if you can cross cancel. When you're cross canceling, you're looking at a numerator and a denominator. So 3 and 5, if we look at 3 and 5, there's nothing we could divide both of those by. However, you could divide 2 and 4 both by 2. So 4 divided by 2 is 2, and 2 divided by 2 is 1. Then you multiply like normal. 3 times 1 is 3, and 2 times 5 is 10. So cross-canceling saves you the step of simplifying, but you get the same result. Make sure that you don't ever try and cross-cancel numerators with each other. It's only those diagonal numbers that you can cross-cancel. So you cross-cancel a numerator with a denominator. Now let's look at division. We're going to divide 2/3 by 3/4. And you know what's funny about dividing fractions is that you don't. We don't divide fractions. Instead, we copy the first fraction, we change division into multiplication, and we flip our last fraction. So we copy the first 2/3, we change division into multiplication, and we flip the last fraction over. So it's now 4/3. And now we multiply like normal. 2 times 4 is 8, and 3 times 3 is 9. And that can't be simplified, so 8/9 is our answer. When dividing fractions, just remember CCF. Copy the first fraction exactly as it is, change division to multiplication, and flip the last fraction. Order of operations. Order of operations is a set of rules that dictates the order in which we must perform each operation in an expression so that we will evaluate it accurately. The order of operations does just that. It brings order into solving or evaluating an expression. Without the order of operations, everyone who solved an expression like this or evaluated an expression like this would get a different answer. And so there would be chaos. And we can't have that in math. So we have the order of operations to tell us what order to do things in. The most common mnemonic device used to remember this order is PEMDAS, or please excuse my dear Aunt Sally. And it's in order of the operations that should be done from first to last. So P is the parentheses, which means parentheses are always done first. After we're done with parentheses, we then move on to exponents. E is for exponents. So if there are any exponents in your expression that you're evaluating, you'll do those or simplify those after you've simplified everything in the parentheses. Our last two sets are special. M and D is multiplication / division. The reason they're on the same line together is that you don't do one before the other. It's not like you always multiply before you divide. What it really is you multiply and divide in order from left to right in your expression. So looking at your expression, we would divide first before we would multiply, because when reading from left to right, the division shows up first. And it's the same thing with AS, which stands for addition, subtraction. You won't always add before you subtract. You'll again work those from left to right. But you will always multiply and divide before you add and subtract. So addition and subtraction should be the last things you do. Now if you have addition, subtraction inside your parentheses, then of course you'll do that first because everything in parentheses gets simplified first. Let's apply these rules to this example. We always start with parentheses. Looking at our expression, we've got some parentheses here around 2 plus 3. So we have to start by adding 2 plus 3. that means nothing else in our expression is going to change. 5 plus 20 divided by 4 times 2 plus 3 is 5 squared minus 6. Now we go back to our order of operations to see what we need to do next. We've done our parentheses, so now we need to look and see if we have any exponents we can simplify. And we do right here, 5 squared. So that's the next operation we need to do. So bring down the 5 plus 20 divided by 4 times 5 squared is 25 minus 6. And we go back to our order of operations. We've done all of our exponents. So now we're moving on to multiplication and division. Again, from left to right. So we start on the left and work our way right, looking for multiplication and division, and we find it, which means we need to divide first, not multiply. So we have 5 plus 20 divided by 4 is 5 times 25 minus 6. So we've done our division. So now we're going to look for more division and multiplication from left to right. And we see that we have multiplication. So that's the next thing we need to do. So we bring down our 5 plus 5 times 25 is 125 minus 6. We're done with all multiplication and division, so we'll consult PEMDAS again. We're done with that. Moving on to addition, subtraction. And again, we work these from left to right. We won't always add before we subtract. We'll just do it in order from left to right. So from left to right, we see addition first. 5 plus 125 is 130 minus 6. And then we do the only thing left to do, subtract. 130 minus 6 is 124. And finally, we've evaluated our expression using the order of operations, or PEMDAS. Scientific notation. Scientific notation is used to write larger numbers in a shorter form. And the form is a times 10 to the n, where a is a number that is greater than or equal to 1, but it's less than 10. And n is the number of times we must move the decimal, and in which direction. Let's take this number, 230,400,000. It's a pretty big number. We can write this in scientific notation by taking our decimal, which is at the end of our number, and moving it 1, 2, 3, 4, 5, 6, 7, 8 places to the left, so that our number is now 2 and 304 thousandths. And you see my a is a number between 1 and 10. 2 and 304 thousandths is greater than or equal to 1, but less than 10, times 10 to the 8th. And this number is the same as my original number. We can also use scientific notation to take very large decimal numbers and write them in a shorter form. We do the same thing. Our a has to be greater than or equal to 1 and less than 10, which means we need to move our decimal 1, 2, 3, 4, 5 places to the right, so that it becomes 2 and 304 thousandths times 10 to the negative 5. And that negative exponent lets you know that that's a very, very small number. It's a decimal. It's less than 1. Whereas a positive exponent tells you that it's a very large number. We can use these exponents to compare our numbers very quickly and easily. Looking at these two numbers in scientific notation, I can tell that 1 51/100 times 10 to the 5th is the larger number because it has the larger exponent. So it's a great method for very large and very small numbers.
ACT, math, trigonometry. The general equation for a circle is the quantity of x minus h squared plus the quantity of y minus k squared equals r squared. So here, h and k are the coordinates for the center of the circle on a coordinate plane. And then r is the radius of the circle. Now, we have something called unit circle, which has a radius of 1, and the center is at the origin. And the origin is where the x-axis meets the y-axis, which is right there, in the center of the coordinate plane. And so the coordinates for the origin is 0, 0, because it's at point 0 on the x-axis and point 0 on the y-axis. And so if we were to plug the numbers 0 and 0 into into h and k, then we would be able to simplify this equation. And then also the radius is 1, so we can plug that in to r right there. So we can go ahead and simplify this equation to get this right here, because since h and k are 0, we can take those out of the way, and then we just plug 1 into r, we square it, and we still have 1. So this is the equation for a unit circle. Now, we have something called standard position, which is the position of an angle of measure, blank, whose vertex is at the origin. So right here, you see this angle, and so I'm just going to label it with the angle symbol. We don't know what the angle is. But the vertex right here is at the origin of this coordinate plane. And then the initial side crosses the unit circle at the point 1, 0. So this right here is the initial side, and it meets the circle right there, crossing the circle at point 1, 0. Now the initial side is always going to cross the circle at point 1, 0. And the reason that it's always going to cross it at point 1, 0 is because the initial side always has to be on the x-axis of the coordinate plane. And so in order to do that, it must be on the y-axis at point 0. And then the terminal side, which is the other side, this side right here, this is the terminal side, it crosses the unit circle at some other point. And so we label that point AB. So it meets it right there, and we label that AB. Now there's a few things we can conclude from this setup. The sine of the angle measure equals B. The cosine of the angle measure equals A. And then the tangent of the angle measure equals B divided by A. So those are a few things to keep in mind. And so this is a look at unit circles and standard position.